Hey everyone, welcome to the session by IntelliPath. The entire world is a big data problem. Managing and scaling this huge amount of data we see every single day is a problem even to the most renowned big data architects out there. But PySpark aims to do this very easily, and in this session we're going to learn exactly that. We'll have a quick introduction to PySpark and learn PySpark in depth at the same time. Well, before we begin with this session, make sure to subscribe to the IntelliPath's YouTube channel and hit that bell icon so that you never miss an update from us. So here's the agenda for today. We'll begin by checking out a quick introduction to Spark, and followed by this we'll check out the architecture and the components of Spark. After this, we can check out all the various methods of deployments there are, and then we can check out everything there is to know about RDDs and the operations associated with them. After this, we can check out the installation of Spark and some fundamentals along with the same. And after this, we can take a quick look at a demo, an interactive demo where you can get your hands on with code and then learn at the same time. And after this, if you guys have any queries, make sure to head down to the comment section below and do let us know, and we'll be happy to help you out there. And if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. Well, without further ado, let's begin the class.
Apache Spark is one of the most widely used frameworks when it comes to handling and working with big data. On the other hand, Python is one of the most widely used programming language for data analysis, machine learning, and much more. So why not use them together? This is where Python with Spark, also known as PySpark, comes into the picture. So let's start with our very first topic, Introduction to PySpark. You know what? The average salary of an Apache Spark developer is around $110,000 per annum. So there's no doubt that Spark is used in industry a lot. Now when it comes to Python, because of its rich library set, it is used by majority of data scientists and analytics experts today. So combining both the Python and Spark was a major gift to the community. Spark was developed in Scala language, which is much like Java. It compiles the program into bytecode for the JVM for Spark Big Data Processing. So to support Spark with Python, the Apache Spark community released PySpark. So guys, what do you think a PySpark is? Any rough idea, anyone? Okay, fine. I'm assuming that you guys know that it is something which has to deal with both Python as well as the Spark, right? Since I already told you that Python is an open source, powerful, high-level and object-oriented programming language, and yes, in terms of its syntax, it's way easier to use and read when compared to other programming language. On the other hand, the Apache Spark is an open source, general-purpose distributed computing engine which is used for processing and dealing with large amount of data. So here comes the PySpark. It's a collaboration of Apache Spark and Python. It is an API for Spark which easily integrate and work with RDD using the library called Py4j. So let me tell you, PySpark is an API where you merge the simplicity of Python with the power of Apache Spark in order to tame the big data. For those of you who are already familiar with Spark and the concept of RDDs, for you guys, you can think of it as a Python API for Spark which easily integrate and work with RDD using a library called Py4j. This PySpark, it offers a PySpark shell, which links the Python API to the Spark core and initializes the Spark context. I hope by now you guys have a brief idea of what is PySpark. Alright? So let's move ahead and let me tell you about some of its advantages. This will help you to know more about why you should use PySpark. So like we can see here, we have speed, powerful caching, real-time computation, deployment, and polyglot. So on number one, we have speed. So when you compare it with the traditional large-scale data processing, it's definitely 100x faster than them. Alright. In terms of powerful caching, well, PySpark will give you a powerful caching with disk persistence capabilities. On third, we have real-time computation. Well, there's a plethora of data which need to be processed in real time. Let me tell you a fact. You know what? Every minute, around 48 hours of video is being uploaded on YouTube. Twitter gets around 98,000 of tweets and more than 168 millions of emails are sent every single minute. Well, these data comes in bits and pieces from many different sources. It can come in various forms like words, images, numbers, and so on.
Just a quick info, in case if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. The link is given in the description box below, so make sure to check it out. And on that note, let's get back to the class.
So Twitter is a very good example of words being generated in real time. We also have websites where statistics like number of visitors, page views, and so on are being generated in real time. There's so much data and they're not useful in their raw form. We have to process it and extract insight from it so that it becomes more useful to us, right? So this is where Spark Streaming comes into picture. It is exceptionally good at processing real-time data and is highly scalable. It can process enormous amount of data in real time without skipping a beat. Alright. Next feature we can see over here is deployment. Well, you can deploy PySpark through Mesos, Hadoop, or even through Spark's own cluster. Alright. Next we have is Polyglot. Well, simply it means that it supports multiple languages like R, Python, Java, and Scala. It basically provides the shell and Scala and Python, which you can access through the bin folder of both Scala as well as the Python. Alright. A question might arise in your mind, like under which situation should I use Python? Or under what scenario should I go with Scala or Java or R? Alright. So let me tell you a fact. The most used programming language with Spark are Python and Scala. Alright. So now if you are going to learn PySpark in this tutorial, it is important that you should know why and when to use Spark with Python instead of Spark with Scala. So let me just compare Python and Spark with some parameters. This will make things clear for you to decide. So our first parameter is performance speed. Python is comparatively slower than Scala when used with Spark, but programmers can do much more with Python than Scala because of its easy interface that it provides. On the other hand, Spark is written in Scala, so it integrates very well with Scala, making it faster than Python. Alright, so next we have is the learning curve. Python is known for its easy syntax, and being a high-level language, it makes it easier to learn. Whereas Scala has an arcane syntax which makes it hard to learn, but once you get a hold of it, you'll see that it has its own benefit. Alright, next is the data science library. Python supports multi-data science and machine learning libraries. But on the other hand, Scala lacks proper data science library and tool. Scala does not have proper local tools and visualizations. Alright. Finally, the last parameter is complexity. So Python API has a simple yet easy and comprehensive interface. Whereas on the other hand, Scala's syntax and the fact that it produces the verbose output is why it is considered a complex language. I hope the things are getting clear to you. So before we dive deeper into the PySpark concept, let me tell you about how big tech giants like Yahoo, TripAdvisor, Alibaba, and other big multinationals are using PySpark for them. Well, Yahoo uses Apache Spark for its machine learning capabilities to personalize its news and web pages, and also for targeting advertisement. And also for target advertising. They use Spark with Python to find out what kind of news users are interested in reading and categorizing the news story to find out what kind of user would be interested in reading each category of news. Next is the TripAdvisor. Well, TripAdvisor uses Apache Spark to provide advice to millions of travelers by comparing hundreds of websites to find the best hotel price for its customer. The time taken to read and process the reviews of the hotel in a readable format is done with the help of Apache Spark. Alright, let's discuss about Alibaba. Well, Alibaba, I guess most of you have heard about it, right? It is one of the world's largest e-commerce platform and runs some of the largest Apache Spark jobs in the world in order to analyze hundreds of petabytes of data on its e-commerce platform. Alright, so I guess now you have an idea that how PySpark is being used in the industry, right? So before I continue, has anyone any doubt up till here? If yes, please add it over to the comment section below and we'll try to reply them at the earliest. So guys, if you're a mobile viewer, get ready with your laptop because now we'll proceed with the installation part. So let's install PySpark in your system. Just to keep it real, just in case you are stuck, you'll find many installation reference out there on the internet, which you can just go ahead and refer to and get installed. So guys, in this tutorial, I'll be teaching you how you can install PySpark on your Windows machine. Alright, if you're a Linux user, add your email ID below and I'll send you the installation step for it. You can just follow it and install it on your machine. Fine. Well, before we actually proceed with the installation part, there are some prerequisites required for PySpark installation that you must know. So as a part of prerequisite, you must have the Jupyter Notebook installed on your machine and you must have an updated version of Java. Alright, so let's just open google.com and just search for download PySpark. Well, I'm assuming that you guys have installed the prerequisite for this session. So proceeding ahead, let's download the Spark. Just Google it, download Spark. The very first link which you'll get is the Apache Spark link. Just click over there and it will redirect you to the Spark Apache website. As you can see over here, the Spark release is 2.4 of November. It's very recent. And the package type which I'm selecting is pre-built for Apache Hadoop 2.7 and later. You have other options available over here. So I'm selecting pre-built for Apache Hadoop 2.7 and later. And finally what I'll do, I'll just click over the download link over here. It will redirect me to a different page where I can see over here it's a mirrored link for me. I'll just click it and my download will start. I think it's a pretty big file. So yeah, it might. So yeah, it's a pretty big file. Just make sure that you have a very good internet connection if you are downloading it. For now, I'll cancel this as I've already downloaded this file. So let's cancel it. Let me just show you where I have downloaded it. Under downloads, I have this file. Spark 2.4 Ben Hadoop 2.7. Alright.
Just a quick info, in case if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. The link is given in the description box below, so make sure to check it out. And on that note, let's get back to the class.
Just unzip it, extract files. I'll extract. Just extract the files. The files I extracted, I'll just save it somewhere. Like, let's save it in the D. Okay. By the time it does save it, just open your CMD. So our next step would be to edit our environment variable. So let's create some environment variable using the setx command. My first variable is spark underscore home. And after that, I'll specify the path of my Spark file. So this is the path. Let's paste it. Done. Okay. Next, I need another environment variable as Hadoop underscore home. Then again, specify the path of the file. Hit enter. Done. Now, since I want to launch my PySpark shell in Jupyter Notebook, so I need to define two more parameters over here. PySpark driver Python and PySpark driver Python OPTS. Alright. This will help me to open the PySpark shell in Jupyter Notebook. So I'll write setx PySpark underscore driver underscore Python and IPython. Hit enter. Done. And my next parameter is setx PySpark underscore driver underscore Python underscore OPTS and notebook. Hit enter. Start. Alright, let's close this terminal. Now let's open a new command line prompt. Now my first task would be to redirect to this bin folder. Alright, so this is the path. Let's copy it. Jump to the D directory. CD space. I want to go over till bin. So yeah, so this is my path. Hit enter. I'm in bin. Now my next step would be to execute PySpark with the command PySpark. I'll use a master parameter for setting the master node. And since I want 2 cores for local testing, so I'll specify master local. How many cores? I need 2 and hit enter. So what it will do, it will open me a Jupyter notebook on my local host. So yes, we have successfully installed PySpark on our machine. If you are facing any issues, comment it below with the error message which you got, and I'll try to resolve it for you. Okay. So for now, just click on new, select Python 3, and it will open a tab where you can write your PySpark code. Alright. So this is the Jupyter notebook with Python 3 where I'll be writing my PySpark codes. Alright. So now is the time that we start and learn with the fundamentals of PySpark. So now the installation is complete, so I guess we should proceed with the fundamentals of PySpark. So as a part of PySpark fundamentals, so we have Spark context, Spark conf, Spark file, RDDs, data frame and MLlib. So I'll start with Spark context. Well, it is an entry gate for any Spark derived application or functionality. Let's see in detail what exactly it is. So when we run any Spark application, a driver program starts, which has a main function, and your Spark context gets initiated here. The driver program then runs the operation inside the executors on worker nodes. Now this PySpark, it uses Py4j. This Py4j enables the Python program running in a Python interpreter to dynamically access Java object in a Java virtual machine and create Java Spark context. By default, PySpark has Spark context available as SC. So creating a new Spark context won't work over here. Alright. Let's move ahead. So here are some of the parameters related to Spark context. We have master, app name, Spark home, serializer, gateway, con, PyFiles, environment, JSC, profiler CLS, batch size. Among all of these, only master and app name are the one which I use most frequently. So for this tutorial, we'll focus on just 2 of them. The master represents the URL of the cluster it connects to, whereas the app name is nothing but the name of your job. Let me show you this with an example. Let's open our Jupyter notebook. So let's write our very first PySpark code. From PySpark, import PySpark context. Alright. And next we'll define a SC as Spark context. And inside this, my first parameter would be the URL. My URL is local. And my next parameter is the name of my application. I'll name it as anything like my app. So I guess we are getting an error like cannot run multiple Spark context at once. Alright, so you can resolve it just by writing sc.stop. Okay. Hit enter and let's reload it again. Execute it once more. Yeah. So as you can see here, my error is gone and the statement is executed. Alright. So what I did over here, I defined the URL and the app name. Now this parameter, it cannot be changed throughout the program. Alright. So alright, this was all about Spark context. So moving on ahead, let's see another PySpark fundamental. So on the PySpark fundamental list, next we have is this Spark conf. Well, it is used to provide a configuration to run Spark application on local machine or cluster. So what exactly is Spark conf? Well, to run a Spark application on a local or a cluster, you'll have to set few configuration and parameters. And this is where Spark conf comes into picture. It provides the configuration to run a Spark application. Initially what we do, we create a Spark conf object with Spark conf function, which will load the values from Spark. Now you can set different parameters using the Spark conf object, and once you set the parameter, 30 minutes, half an hour. Initially, we'll create a Spark conf object with Spark conf, which will load the initial values from Spark. And once set, their parameters will take their priority over the system properties. Alright? Remember, once we pass the Spark configuration object to Apache Spark, it cannot be modified by any user. Thus, it becomes immutable. So we have set master, set app name, get, set Spark home. Alright. So set, it is used to set the configuration property. You specify two parameters over here, key and a value. Fine. In set master, you specify the master URL. In set app name, you set an application name. Finally, there's a get. Get is used to get the configuration value of the key. And finally, there's a set Spark home, which is used to set this Spark installation path. Let me show you this with an example. This should make things easier for you to understand. Alright. So let's move ahead. Alright. So let's jump to our Jupyter notebook. So let's define our configuration file. For this, I'll use from PySpark .conf import Spark configuration. Alright. Next is from PySpark.context import Spark context. Alright. Next, what I'll do, I'll define a variable as conf, and in it, I'll define my Spark configuration function. Dot, I'll set the app name as set app name, name of my app. I'll name it as PySpark demo app. And I'll set the master as local 2. Fine. Now let me show you how this get function is working. So since I defined this conf variable, so I'll just write over there conf.get. Inside that value, my value is what? Spark.master. Spark.master. So what it will do, it will give me the master URL which I have already set. Fine. Let's hit enter. As you can see, we got the URL as local2. Fine. Since I have already set my master URL as local2. Now what if I want to check my app name? So configuration.get spark.app dot name and hit enter. So my Spark application name was PySpark Demo App.
Just a quick info, in case if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. The link is given in the description box below, so make sure to check it out. And on that note, let's get back to the class.
Alright, so I guess we can move ahead. So next in the PySpark fundamental we have is this Spark file. The Spark file, it helps in resolving the path of files added to Spark. Alright, so what exactly is this Spark file? Let me first tell you what it is. So whenever you have to upload your file in Apache Spark, you can upload it using the sc.add file, where sc is your default Spark context, remember? Right. And whenever you want to retrieve the path on a worker, you can get it using the sparkfiles.get. The Spark files is used to resolve the path of the file added through Spark context.add file. Okay. Now let's talk about its class method. Spark file contains two types of class method, get and get root directory. Get is used to get the path of that file that is added through the Spark context.add file. And get root directory function is used to get the path of the root directory added through sc.add file. Fine. Let me make things more clearer with a demo. Alright, so let's check out the demo for Spark files. So from PySpark, import Spark files. Fine. Next, from PySpark, I want to import Spark context. Next, what I'll do, I'll define my path. Path equal os.path.join, and inside that I'll define the path and the file name. So my path is, this dspark ben. Okay. So yeah, this is my path and the name of my file is, just copy it, and the name of the file is fortune5002017. Alright, so since I have defined my path, so my next step would be to add the file. So sc.add file. From where? From this path which I have already mentioned above. Now let's hit enter. Oh, what's the error? Okay. So yeah, it got executed. Fine. Now let's check for its root directory. So let's add another. Let's check for its root directory. Spark files dot get root directory. Define it. Let's see. So there's my root directory. Alright. So moving on ahead, in PySpark fundamentals, we have RDDs. Well, there's a very important concept that you have to learn. Alright. It stands for Resilient Distributed Dataset and is a building block of every Spark application. So what is RDD? RDD stands for Resilient Distributed Dataset. Resilient as if the data in the memory is lost, it cannot be recovered. That is, it's fault tolerant behavior. Next is distributed. The data is chunked into partition and is stored in memory across the cluster. And finally, it's the dataset. That is, initial data can come from a file or it can be created using the program. Fine? Alright. So next we have types of operations in RDD. Well, we have two types of operation in RDD. One is transformation and other is action. Let's see about them in detail. So what is transformation in RDD? Well, these Spark RDD transformations are functions that take an RDD as an input and produces one or many RDDs as output. They do not change the input RDD, since I already told you that RDDs are immutable and hence you cannot change it. So what they do is they always produce one or more RDDs by applying the computation they represent. For example, map function, filter, reduce by key, etc. These transformations are lazy operation on an RDD in Apache Spark. It creates one or many new RDDs which executes when an action occurs. Hence, transformation creates a new dataset from an existing one. Certain transformations can be pipelined, which is an optimization method that Spark uses to improve the performance of computation. Next comes the action operations. An action in Spark returns the final result of RDD computations. It triggers the execution using lineage graph to load the data into original RDD. Thereby carry out all the intermediate transformation and return final result to the driver program or write it out to the file system. The lineage graph is dependency of all the parallel RDDs of RDD. Action are RDD operations that produce non-RDD values. They materialize a value in a Spark program. An action is one of the ways to send result from executors to the drivers. Few functions which are a part of it is like first, take, reduce, collect, and so on. Alright. So using transformation, you can create RDD from an existing one. But when you have to work with the actual dataset, at that point you have to use action. Remember, when the action occurs, it does not create new RDD like transformation. Thus, action are RDD operation that gives no RDD values. But in turn, what it does, it stores the value either to driver or to external storage system, thereby bringing laziness of RDD into motion. Well, here is a summarizing image for you. As you can see, when you apply transformation operations like map, filter, sort by or anything, so what it does, it creates a new RDD. Whereas on the other hand, when you have to perform actions like using first, take, etc., then your existing RDD is saved as a file. Alright? So I think you guys might have a question in mind like when you guys should use RDD. Right. Well, here are some of the scenarios under which where RDD is most preferably used. First is the unstructured data. When your data is unstructured, for example, in case of a media stream or stream of text, you can use RDD. Second is the no schema. Well, this is the case where you don't care about imposing the schema, such as the columnar format or while processing or accessing data attributes by name or column. Fine. Next is the data manipulation. That is, you want to manipulate your data with functional programming construct that domain specific expressions. And finally, we have the low level transformation. That is, you want low level transformation in action and control your data set. Alright, so these are the scenarios under which you can use RDDs. So next on the PySpark fundamental, we have data frame. So this was all about RDD. If you have any doubt, don't hesitate in adding them in the comment section below. It will be beneficial for you as well as for the other learners. Alright. So in the next PySpark fundamental, we have data frame. Data frame is a buzzword in industry nowadays. People tend to use it with many popular languages used for data analysis like Python, Scala, and R. So why is that everyone using it so much? Well, data frame generally refers to a data structure which is tabular in nature. It represents rows, each of which consists of a number of observations. Rows can have a variety of data format which can be heterogeneous, whereas a column can have the same type of data type, that is homogeneous. Data frame usually contains some metadata in addition to the data, for example, the column and the row name. Okay? We can say that data frames are nothing but two-dimensional data structure similar to a SQL table or to a spreadsheet. Fine. I hope that data frame is clear to you guys. So moving on ahead, in the end we have the MLlib. MLlib is a machine learning API of Spark which in turn supports various machine learning algorithms. It is a machine learning library that is provided by Apache Spark to make the machine learning scalable and easy. It provides various tools for machine learning algorithm, featureization, pipelines, persistence, and utilities. Few machine learning algorithms which are a part of it are classification, regression, clustering, collaborative filtering, dimensionality reduction, and others. Alright. So, as a part of featureization, they have feature extraction, transformation, and selection. In pipeline, they have a tool for constructing, evaluating, and tuning machine learning pipelines. Alright.
Spark Core forms the vital component of Spark, where it talks to all of the other modules for us, keeps in check with the other submodules. You have Spark SQL, you have Spark Streaming, you have MLlib, which is the machine learning library. Then we have Graphics, which is used for graph processing. And again, streaming is for live streaming, and SQL is to perform unstructured data processing, data access, and data manipulation as well. So to bring all of this under one particular umbrella, we have Spark Core. As I've already mentioned, this forms the the base of the Spark engine, guys. So our Spark Core, as we already know, it contains all of the basic functionalities of Spark, right? So we have many things which needs looking at. Consider fault recovery, memory management. You need task scheduling. Then you're gonna need algorithms. There are many task scheduling algorithms. There is first in, first out, round robin. There's so many algorithms, right? So you need something to stay in constant touch with that, and to make it readable for both the program and the user as well. Again, as you've already checked out in the OOPS concepts, abstraction forms a major part of our learning, right? So again, the major abstraction concept here for the Spark Core is something called RDDs, guys. I'm not sure if you guys are familiar with what RDDs are. If you're not, don't worry, I'll be walking you guys in detail about it in the same module. And basically it is a data unit, but we'll be anyway checking it out in the next couple of slides. So again, yeah, Spark Core provides many APIs, which is application programming interfaces for processing. Processing structured data is pretty much easy, but going about working with unstructured data is not impossible per se. But then at the end of the day, if it's unstructured, think about it, right? So structured versus unstructured, the example that's top of my head right now is having a clean bedroom and a living room versus a very shabby room where you've thrown all your dresses around, and then you're in a hurry to pick up your dress and you have no idea where you're looking at, right? So similarly, that's again unstructured data. The next component will be revising is Spark SQL. Again, Spark SQL already provides us APIs, and we already know we can work with structured data using SQL. And again, people who have an SQL valid background and people who have been working on it for a long time, then pretty much can make use of SQL commands with to talk with Spark and go about querying their language and data gathering, data manipulation, and storage as well. So again, with Spark SQL, guys, there is many data sources which you can have, right? Usually most of the time, all of the data sets are pretty much CSV files. And again, we have JSON queries that we can pull up, and we can have requests, and we can pull up a lot of data using that as well. Then we have Parquet, we have Hive, we have Cassandra, and guys, there's lots of data sources, a lot of abstraction tools where we can keep pulling in data at it is at our wish, right? So pretty much that's what I wanted to convey here. And with SQL, it really makes it easy. And then if you already know how you can go about programming with SQL, it makes your life even more easier because it is giving you a ready to use API to work with Spark. And next up, we have the Spark streaming engine, guys. So this basically provides us with really low latency and high quality streaming. So basically, we need processing tools which go about giving us this result, right? So Spark streaming has again APIs which pretty much give us direct access, fast access, and most of all, we'll be covering an entire module about streaming, so don't worry about it in depth. But at this point of time, what I want you guys to know is that to give you a quick idea of how it works. So basically, it gets all of the live input data streams, right? So it has continuous data flowing into it. To handle this particular data, what Spark streaming usually goes about doing is it pretty much splits all of these data into certain tiny snippets, and we call it batches basically. So basically it goes about dividing data into batches. To give you an example, consider Twitter, right? So Twitter is usually, I wouldn't say spam, but Twitter is bombarded with so many amount of tweets from everyone around the world, right? So imagine all of the data being generated at Twitter. So if you have to process this in real time, it is going to be a little tough. But then we can go about almost pushing for real time requirements. That's what we call by near real time. And this can be done. You can have logs generated, you can work on the logs, and you can perform analysis on the data as well. So you can do sentiment analysis and whatnot using the MLlib as well. So to go about doing this and to access that near real time data, right, so we're pretty much going to need Spark streaming, guys. And next up, coming to the MLib, guys, this pretty much is the core for Spark's machine learning and artificial intelligence concepts. We're already familiar with the hype which goes on about machine learning and artificial intelligence, right? So, to just take a quick detour, if you guys remember back in the day, I think we were being told that machine learning and artificial intelligence will one day revolutionize the world. Guys, it pretty much is already revolutionizing the world, right? I mean, it has been so subtly integrated into our world that we don't even realize it's there anymore. Look around you, probably, you can say, if you have an iOS device, you can pretty much go about saying, "Hey Siri," and that's artificial intelligence working for you. So everything from pretty much turning on your lights at home, turning on the air conditioner, putting rockets into moon and Mars as well. So we have machine learning everywhere, and it's been ever so subtly implemented that it's not pushed into our face. The concept is not pushed into our face, and it's really fun to work with. So anyway, coming back, guys, this particular library, right? So the machine learning library with Spark, it has so many inbuilt libraries which pretty much give you access to the plethora of machine learning algorithms which are ever so present with, in the case of machine learning and its concepts. And to give you a couple of names, machine learning algorithms, guys, we have classifications, we have regressions, we have clustering, we have collaborative filtering, right? So we have linear regressions. There's so many algorithms that you have to know and work with when it comes to machine learning. So in that particular case, MLlib pretty much has us covered here as well, guys. Also, machine learning library, right? So it provides various techniques as well. It's not the only thing where it provides a couple of libraries for us and then we go about doing it on our own without any guidance. No. So it provides us a couple of techniques of how we can go about pre-processing our data. Because at the end of the day, data might be structured, unstructured, right? So we converting this particular data into something usable, right? So that usable part is what we call information. So data as it is, as it stands, Spartan, there's pretty much nothing you can do about it. So it is clustered, it is, unstructured, and at the end of the day, it might not be what you're looking for. So consider, data if you want like a mug of coffee, guys. So if I give you the coffee powder, I give you a cup of milk, I give you sugar, all separate in 3 containers. Well, it is still coffee, but at the end of the day, you cannot drink from each and expect the same coffee taste, right? So that is data. And let's say you brew up a really good cup of coffee as soon as you mix up all of that and do all the process, and then that becomes information, right? So this pretty much, again, for coffee to pretty much take it from the plant, the coffee plant, and then to get it roasted and ready to grind, this can be another good analogy for data pre-processing as well, guys. And next up we have graphics. So pretty much there's, as beginners, I guess you guys might be interested in graphing out a couple of data as well, and basically it's visualization, guys. So whenever I've spoken to a beginner, that person as a learner, he prefers to find out more about a language, more about a code, if it looks really good. So graphics is, again, pretty much you can graph out everything you want to, and basically at the end of the day, graphs look really nice to look at and work with, right? Most of all, it provides really good analysis and it supports computation for large amounts of data, right? So again, I've been giving you analogies with simple terms to just put the concept in your heads. But at the end of the day, you need to realize that the data which you'll be working with at the end of the day is huge. So yeah, and at the end of the day, instead of looking at a million numbers, it would be really nice to look at probably 10 graphs, right? Think about it. And they pretty much come with a variety of graphing algorithms and a lot of computation techniques as well. And these are mainly used for disaster recovery systems, and something like, say, after a hurricane hits and you need to find out what's going on, what is the level of damage, the the population who were affected by it, and so on. And a couple of page ranking algorithms have used graphs, as well as I've seen a lot of financial fraud detection systems. And most of all, I think graph, the first thing, the most important thing that comes into my head is pretty much, think about it guys, stock market, right? So if you keep looking at numbers, then sure, that'll work too. But again, looking at graphs, if you're a trader, you will pretty much figure out how important graphs are, right? So graphics is pretty much the Spark equivalent for that. Here is an abstracted quick view of what everything looks like. So Spark components, again, we already know that the programming languages supported by Spark are pretty much Scala, R, Java, and Python, where a couple of people prefer Python over Scala just for good readability, easy learning, and a lot of applications as well. With terms of library, we have seen SQL, MLib, graphics, and streaming as well. And to talk to all of these components together and to hold one management engine, we have the Spark core. And then we have something called cluster management tools as well. We've already checked out what Yarn is. So Yarn is basically yet another resource negotiator. And so to have your data in clusters, to access the data from these clusters and you to work with, pretty much you're going to need Yarn to talk to Spark as well. And then we have Apache Mesos. Again, Mesos is similar to Yarn, but it pretty much gives you very good functionality as well. And then we have Spark Scheduler, guys. Again, this is another cluster management tool, which I think a majority of users who have real-time dependencies go about using it. Then for storage, you're already familiar with HDFS, Hadoop file system. Then we'll be checking out, we already know that you can pretty much convert all of our data into the Hadoop file system requirements and pick it up from each individual nodes in a network. But Apache will also support a standalone node as well. So let's say you're experimenting and you have no instance where you connect to multiple nodes for your clustering requirements. You can pretty much go about doing it in a standalone node as well. And to move it to cloud, I think Amazon EC2 does a good job to pretty much help you with storage and to move everything to the cloud as well. And support for relational database management systems and NoSQL is of worthy mention here as well. So I would recommend you quickly probably pause the screen or something and just glance over all of these concepts, because these again form the major foundation to go about learning Spark. And to later down in the day, since you're going about mastering this entire thing, you might not require to keep coming back to this diagram, but at this point of time, I would highly recommend you to be aware of these concepts, guys. So without further ado, let's quickly check out Spark architecture, guys. So I pretty much have a very simple diagram here to denote what happens. So we have something called as the driver program in Spark. So driver program is the link between you as a programmer and Spark's program. So all the data that you input, all the data that you need manipulated, and to go about working with it, you need Spark to understand your data, right? So again, our driver program, which consists of this concept called as Spark context, is pretty much used for this. So again, thinking about drivers, right? So think about it, recall if you're familiar. So if you have a brand new hardware where you need that hardware to talk to your machine, you need the hardware to talk to a software, and at the end of the day you need to use that. So basically you'll be using a driver there as well, right? So again, the concept is again pretty similar and simple out here, guys. So coming to Spark context pretty much forms the main entry point for any functionality in which you'd go about doing in Spark. So basically, at the end of the day, our Spark context is used to create what we call RDDs. Again, I'll walk you through it. To create accumulators, we used to broadcast a couple of variables and all of that. But one thing that at this point of time in the introduction that I would like to tell you guys is, again, you need to know that for every single instance of Spark running, a Spark core running, you need to have only one Spark context. So if you have more than one, again, you cannot run it side by side and you will get a error, guys. So one Spark context for every single program and you'll be good to go. So again, all of the data that I've inputted pretty much goes into our cluster manager, where we have a couple of management tools that we looked at in the previous slide, where again, this depends on you. If you're pulling your data from the cloud, you're pulling it from a couple of different nodes, or you're pulling it from one standalone node and all of that, right? So the cluster management, I think, forms a very vital part. Because think about it, right? So if you're forcing someone to always use offline data, or say use data only from a machine, then it really doesn't make sense. But then if you give them freedom to pull the data from the cloud, pull the data from another node, pull it from another cluster, cluster is basically the group of nodes and data. So when you give them this amount of freedom, then it would really help scalability, help a lot of users, a lot of developers at the end of the day, right? So cluster management is again customized for your requirement, where you pull out the data based on your needs and all of that. And next we have the worker nodes, guys. So worker nodes are, at the end of the day, it's the endpoints of our Spark architecture, where the data gets converted into information, where we getting the task done. As you can see on your screen, we have something called as the executor, right? So that is what it literally means. So worker nodes again are your endpoints of the system, where you will go about working with it. You will go about you'll be asking your worker nodes to pretty much use the algorithms, learn something, and tell you give you a valid output. So all of that part goes about in the worker nodes, guys. So again, at the end of the day, worker nodes needs to have it needs to be in touch with Spark context for various reasons. Don't worry, I'll be walking you through that in a couple of slides. But that's why you see the big arrows up and down, where it keeps talking to each of the nodes. So it is important that you talk to every single node that you're actively making use of, right? So if you're making use of 10 nodes, but then you're only telling your program that you'll be pulling data from one single node, you know that there are 10, but your program is seeing only one. That really wouldn't make sense. So to make your program, to convince your program to see 10 outputs, and to see 10 inputs, that forms a vital part. So again, as we've already Spark provides a very well defined layer architecture, which makes it really easy for a beginner to learn. And all of these components and all of the layers are loosely coupled, guys. So again, as I've mentioned about the freedom of going about manipulating for your requirements, you are not asked to learn in a very tightly bound environment, where you cannot wiggle around or do something of your own. And I think this makes Spark a little easy. So again, driver program runs on pretty much the master node, what we call of the Spark cluster, which is again the master slave organization, where you need to know at this point that whatever driver program we have, again, it runs pretty much on the master node of the Spark cluster. And so it is basically, it schedules all job execution and negotiates, as I've already mentioned, with the cluster manager. And we'll be using it to translate RDDs into execution graphs as well. So think of RDDs as a simple array at this point of time, and a lot of data, a lot of numbers usually, and all of that. So our the entire architecture here, it makes it easier to pretty much translate this entire RDDs and numbers into graphs, guys. So the driver program, again, it can pretty much split up graphs as well into, it can split up the graphs into a couple of stages as well. So this will simplify your use case when you're going about coding and, working on a very big project, guys. So again, as I've mentioned, the role of the executor is pretty much to take care of all the execution of the tasks that you provide. And every application has to have its own executor, because again, it is not native to what you're doing, and pretty much most of the tasks are different from each other, right? So again, the executor, as I've mentioned, also performs all of the data processing that it needs. It can read data, write data, it can push the data to external sources, it can pull in data from external sources as well. And you can see the small arrows on your left where it talks to the cluster manager as well. So it interacts with a variety of storage systems, and this again makes it easier to go about, guys. So with cluster manager, again, it is the service which is pretty much responsible to gather everything from your driver program, to gather all the data that's required for the executors to work about. And then you can have the standalone cluster manager as well. So pretty much it is one single entity, and you will go about using the standalone cluster manager for your learning journey, because I don't think you would it would be valid to bombard you with a couple of multi-node networks and to go about that way, right? So cluster manager, again, as we already walked you through, it basically depends on what you're doing. So it can be a very simple Spark application, and it can lead all the way to something really fancy, right? So so next up, we'll be checking out Spark deployment modes, guys. There's a variety of Spark deployment modes that we've already talked about, The first most important thing you need to know is that Spark works in standalone mode, right? So we can go about launching the Spark cluster. You do not need any third party cluster manager to work with Spark. Spark is again, I mean, this cluster is basically again used to deploy Spark applications as well. And next we have Mesos. Mesos, again, the most important thing that Mesos can do for Spark is it usually replaces our cluster manager in Spark, the native cluster manager. And it goes about providing a private cluster of data for you, and then it provides a lot of tools as well. Next up, you can have Spark on Yarn, so you can pretty much deploy it on top of Yarn, and usually Spark with Hadoop can enhance Spark's capability by a lot. So it's like this extra masala we put on a dish, right? So put that kind of analogy in your head. So Spark with Hadoop is it plays a major role in upping Spark's game, guys. So that's what I wanted to convey. And we have Amazon EC2 as well. So Amazon has been providing us with a lot of good cloud services these days, and I'm sure you guys already know what Amazon EC2 is, right? In case you do not know, well, basically Amazon EC2, it stands for Elastic Cloud Computing, and so basically, we know what it stands for. So it is a web service that provides, secure, resizable computing capacity, and it does this. I mean, it is not at the end of the day, it is on cloud, right? So it is meant for scalability, and that is how EC2 works. And to push your entire application to cloud is something really nice, guys. I mean, I've personally worked on a couple of projects with EC2 where I've moved a couple of stuff there, and it makes your life a lot easier. Cloud at the end of the day, right? So then we have Kubernetes. Guys, Kubernetes, again, it is an open source chain. So basically, Kubernetes was founded by Google. It was invented by the developers at Google. But right now, it's being maintained by a separate firm. The firm is called Cloud Native Computing Foundation. And sure, Kubernetes is fun to work with as well. So what I want to convey with this slide is that, in terms of Spark and its deployment, you can go about working with it standalone, with Mesos, with Yarn, with EC2, and with Kubernetes as well. So let's quickly have an introduction of how we can run applications on Yarn, guys. So the one thing that I want you guys to note at this point of time is that Spark is already pre-configured for Yarn. So you do not need any other additional configuration to run Spark on Yarn, and I think this is a huge advantage for learners, right? So let's say you have to write a very simple hello world code, but then you have to spend 3 hours to set up your runtime for it. It really doesn't make sense, and probably, yeah, you will do it at the end of the day, but as a beginner, it would not be right to bombard you, right? So the people who have designed Spark have pretty much thought about this already, and they've pre-configured it for Yarn, guys. So we already know Yarn pretty much is used to control resource management. It takes care of all of our task scheduling for us, and even it provides a couple of security features as well. So again, security is a primary aspect for many of the applications that we write, and the developers at Spark have got us covered again. With Spark and Yarn, it is again possible to run any application in any mode, right? So we have two particular modes. We call it the cluster mode and the client mode. So cluster mode is when you need your application to talk to a couple of nodes and pick up the data from a couple of nodes, and to go about launching your application basically into this particular instance, guys. With client mode, again, most of the time you just have one single entity that you have to deal with, and you have to go about working with that entity, processing with the master node will tell eventually what that application needs to do, but then processing the actual data, making use of the data, and then pretty much going about with the goal of your application, and to ensure that the goal is met, right? So again, client mode and cluster mode basically are two ways where you can pretty much launch a Spark application, guys. So the Spark driver, right? So we have something called as a Spark driver, guys. So the Spark driver pretty much it works as a part of our application master. We call it AM, but it's application master. And so the management of this particular Spark driver, the management of our client application in terms of Spark is basically done by Yarn. So the client, as soon as you initiate your application, as soon as you put your application onto deployment, you don't have to worry about anything else at this point, because as we have the Yarn container, again, Spark driver talks to the Yarn container directly. So you just need to have one single process in the Yarn container that will take care of your entire application. The process is what we call, it's called driving your application. So it can go about driving your application. It can request resources from Yarn. It can issue commands to something called as node manager. You can have your Spark executor go about doing the job that it's supposed to do as well, right? So the node manager, again, we've already seen it. Node manager pretty much talks to all of our single cluster events and talks to all of our executors as well. So to allocate the resources and to get the job done and to pull all the data from one single entry point, we have the Yarn container, guys. So again, the resource manager, so the driver pretty much talks to our resource manager as well, where it gets all the resources and it allocates the resources, which is pretty much required to go about doing this as well. So at the end of the day, after the executor runs your task, then the task is complete. It is pretty simple. You just need to know what Yarn container does, what node manager does, and how resources go about being allocated, and a couple of simple processes, guys. So again, when you think about it, right, so in the deployment mode, in this particular deployment mode, the driver again runs on the host where you are providing it with the job, right? So if I'm sitting at my home and I want the job from there, so I push, the terminology we use is push. So as soon as I push the job from there, and basically at the end of the day, the driver needs to run where you're pushing your job from. So the executor will require all of the data. So what it does is it pretty much goes on requesting from Yarn, and Yarn will talk to our application master, and application master will eventually give it all the data it needs. Then Yarn talk to the resource manager will allocate the resources. Commands are sent into the executor, and at the end of the day, it is executed, guys. So quickly jumping on to the next concept, which is Spark Shell. So guys, Spark Shell pretty much is a very, it provides the most simple way to go about learning what Spark actually is. But do not be fooled by the simpleness of shell, because shell programming is again a huge asset for any programmer, because at the end of the day, it is again a very powerful tool which is used to perform in-depth analysis as well. And writing shell command, I personally prefer it to be fun, because of the you can go about interacting with the shell directly, and to get used to it, to see a lot of code. I think for me, Spark Shell is really fun, guys. So our Spark, the shell pretty much, again, it supports three types of interactive shells, guys. So we have Spark Shell with Scala, we have with Python, and with R as well. So we can go about concentrating how it works with Python. Let's quickly dive into what Spark Web UI is, guys. So think about it. What do you think about Spark Web UI, where you can use Spark Web UI, and what you can go about doing it, right? So quickly take a minute to see if something pops up in your head, or probably if you've seen or read about this somewhere else previously as well. So I hope you guys could figure something out. So coming to the concept, the Web UI is again pretty much the web interface of a Spark application, guys. So why would you need a web application? Again, at the end of the day, the UI is really nice, and you would rather have take a look at a quick UI and figure stuff out really fast rather than getting messy, right? Well, mainly it is used for inspection. It is to see what your Spark jobs are doing, what's happening with your particular clusters and all of that, guys. So consider where every single time you create a new Spark context, this will basically tell your application to launch one instance of your web UI. Your web UI can be pretty much on it is on the local host machine, right? So there is this particular ID that you can use it, and you can do a lot of things with it. You can go about working with jobs. You can check out what the stages of your application is. You can check out what the storage, what's the issue with storage, what's going on, how much amount of data your each application needs, so you can go about having your resource allocators allocate that. You can check out the environment in which it's being worked on, right? So a lot of things that you can do, and you will be talking to your executors at the end of the day as well. So web UI is really a fun way to take a look at that. So the jobs tab, again, yes, it is usually used to show all the status of whatever is happening with your current Spark jobs in that particular application, guys. So as I've already mentioned, the Spark context, you will be looking at the context in the job. tab basically. Again, this particular jobs tab consists of usually 2 pages. So it consists of all jobs where you're given, you're presented with a nice to look at list of all the jobs, and then you can go about finding out the details for each individual jobs as well. And later basically the tab which it is used to display your stages per state. Let's say you have your state to be your application is in an active state, it's working, your application is pending execution, your application has completed execution, it has been skipped, or it has failed and crashed, something like that. So to find out all of this, I think WebUI is it's really helpful, guys. And the stages tab again is to tell you basically when your Spark application basically got initialized, guys. So the stages tab that we are checking out is basically used to show that current instance of what's happening. So again, as I've already walked you through the instance, it can be stopped, it can be executing, it can be a lot of stages as well. Basically, you can go about customizing this, but let's not get into the depth right now. Again, the stages tab, it includes all stages page, where this page will tell you the stages of all your applications. Then you can pretty much move into one stage page, and later you have something called as pool paging as well, guys. Coming to storage, well, yes, the storage tab again goes about displaying the information about RDDs. Again, if you do not know what RDDs, I hope I am piquing your curiosity on what they are, and this entire module is pretty much about RDD, so we'll be checking that out in the next couple of slides. Again, in the storage tab, we have something called the summary page, where summary page basically shows us the storage levels and partitions of all of these RDDs, and it shows us the size and the executors which are used for this. Use for partitioning our individual data, organizing the data in a structured way, possibly. And guys, the storage tab, right? So what we're talking about, it includes 2 pages. One is called as a storage page, and the other one is called as the RDD page. The storage page will greet you with all of the data of what your application is consuming, and the RDD page will tell you of what your resilient data sets are, carrying. What's the weight that they're carrying? What's the data that you're presented with? Is the resource present to be allocated, and all of that, guys. Next up, coming to the environment tab. The environment tab again basically displays the values for different configuration, a lot of variables, and your environment as well. Why would you need this? Well, at the end of the day, you can be working with Java, Scala, Python, and you'll be talking to a lot of system properties at the same time as well. To go about, giving you a quick look at everything, I guess this would make it very important, guys. Again, the tab, pretty much as soon as it's created, you have 2 pages, guys. So one is the parent Spark UI, where you will be it's almost like an admin access to your application, let's say. And then you have the app status store, where you can go about coding and finding out what your application is doing at that point of time. And the next important tab is our executors tab, because executors tab will give you one single page, a huge summary of what's going on with your executors, that was basically created for your applications to run. So there's a lot of things it can display, but mainly you'll be concerned with the memory usage, the disk usage, the task that is in hand being processed, and the information that corresponds with it. The storage memory column in the executors tab pretty much goes about showing the amount of memory that particular application is consuming in real time, and it will also show you the memory which is basically reserved for caching couple of data as well. So major caching actions goes on in this stage, where we require faster access or near real-time applications. So our executors tab pretty much give us that big summary there. So moving on, next we can go about having a quick introduction to the PySpark shell, guys. So as we're already aware, PySpark shell, again, it exposes our Spark programming model directly onto Python, and we can map, we can go about using Python with Spark directly. And our PySpark shell pretty much links our entire Python API directly onto our Spark core, and it is used to initialize the Spark context as well. And as I've already kept on mentioning for a while now, majority of the experts, majority of say data scientists, analytics experts, they use Python because it has this amazing amount of huge library where you can pretty much find a library for even one of your custom requirements as well. So, at the end of the day, I'm sure people at Spark had to integrate Python with it, because think about it. So Python gives you access to numerous libraries, and then if you can do all of that along with Spark, hey guys, that's a win-win, right? So integrating Python with Spark was definitely a boon. Yes, I can vouch for that. So yeah, Spark again, it requires Python to be available on the system path, because Spark needs to know where Python is, and to have that unrestrained access, untainted access basically, and that is basically used to run all of the programs, guys. So to quickly give you an idea of what a Spark shell looks like, here is what it looks like on a Windows 10 machine, where you can pretty much go about installing Spark. I mean, installing Spark on Windows is it's very simple, guys. So as soon as you open up your the Spark shell and you go about typing PySpark, you can be greeted with a message which says Apache Spark with Python. And this is how some people might like working with shell and some people might not prefer. I mean, that's personal preference. But sometimes, yes, I still hold my word where I've told working with shell is fun and you'll be learning a lot as well. So next, quickly have an overview of how we can submit a PySpark job, guys. So with in terms of PySpark or Spark in general, it's not that all of our code are independent of each other, right? So sometimes we have this native code dependencies. It can be with other projects. You can have multiple source codes from coming in from multiple directions, and then you need a way to go about packaging them with your application, and you need this code to be basically distributed to every single node on your Spark cluster as well. So for this, we usually, we go about creating an assembly jar file that contains our code and all of its dependencies. So there is a quick requirement for Java as well. And you have Maven again, which can have assembly plugins. And basically, when we're creating your jars or say lists in Spark and Hadoop, so again, these are certain dependencies that we need to know, we need to work with. And again, here's a quick overview as well. So after that, we'll have the assembled jar file, which we can basically call as the bin file, or our Spark submit script, which is used to basically, as the name suggests, to submit our script while passing our jar file as well. So as soon as you hit Spark submit, so this script is basically used to launch the applications that you've just programmed and to push it on the cluster, guys. Again, quick recall, Spark is already pre-configured for Yarn. It does not require any additional configuration to run. Yarn controls all of our resource management, scheduling, and security. It is possible to run an application in any mode, right? Either cluster mode or client mode. So to be launching it in cluster or client mode, all you just have to go about using this simple piece of code. So you might be wondering all the backslashes, right? So if you're going about using shell programming, then you'll be exposed to a lot of slashes as well. So have a quick pause of the screen and try to see if you can figure out. I mean, it is not important at this point of time for you to know what this does, but then just see if you can figure something out, right? So most of your learning happens due to your perspective. So you try to figure it out and on your own, and I think that holds better in memory as well. So go about quickly pausing the screen to see if you can figure something out. And if you cannot, not to worry. Anyway, we'll be checking this out in the next couple of modules. So there, you can get familiar with this as well. So again, this is the steps which you'll be using to going about building the application. So we'll be creating a document. Let us say we'll call it PySpark job.py .py extension, because again, this is a Python file. We'll be storing it on any of our local drives, local machines, and whatnot. As soon as you open the file, yes. So what we're doing here is we'll be printing, hello, this is PySpark, right? So you can upload this particular file into our Cloud Labs local storage, guys. So if you're not making use of a virtual machine at this point of time, you can have this tiny hello world code to be pushed onto our Cloud Labs local storage, and you can perform this particular steps to go about working with it, guys. So basically, as I've already mentioned, to run your application, you will be using Spark Submit Master, and we'll be using the Yarn cluster here. So we're using Yarn deploy, and as soon as you go about using that client your file name.py, it will go about pretty much working with it. And if you can see here, if you can check out the mouse, this is where you have your application output as well. So this is how you would go about submitting a PySpark job, guys. And so how can we go about checking a PySpark job using a couple of Jupyter notebooks? Spark can pretty much go about easily running in its standalone mode that we have discussed, and Consider this tiny example I have on the right for you, right? So this is again Google Colab. I'll be quickly walking you through the same. So in this particular example, we'll be importing PySpark for our usage. Firstly, we'll be installing PySpark. We'll be importing PySpark. We'll be initializing our Spark context. Followed by that, we'll be performing our calculation. So we'll be using the mod function. This is basically our basic, Spark job. And later we'll be using an RDD operation to perform a transformation, guys. I hope I am, again piquing your interest on what an RDD is. So if I have to, give you a small trailer of what RDDs are at this point of time, well, RDDs actually stand for resilient or distributed data set, guys. So RDDs are the fundamental structures of Spark. And every data set in an RDD is again divided into a lot of local partitions, which is needed for each different clusters and all of that. Anyway, we'll be coming back to that. So let me quickly open up my Google Colab so we can walk with our first PySpark job, guys. So this is Google Colab. You can basically access it by typing in collab.research.google.com. And this is basically, guys, at the end of the day, this is just a Jupyter notebook which is hosted on Google Cloud. So you can carry your code easily everywhere. So I've been using Google Colab for a couple of years now, ever since its launch, and I find it really easy. Basically, it's convenience, guys. So all you have to do is to run your code. You type in your code. So our first code is again to basically check the Java version that we require, and as soon as I go and hit the play button right next to it, done. So your code is executed, and you do not have to install Python. You don't have to install the dependencies. You don't have to go about configuring the runtime executor. Nothing. So all you do is type in your code, hit play, and you're good. So that's how simple it is, guys. So basically we have Java version 11 right now, but for our Spark applications, most of the time we prefer Java 8. So I'll be installing selection 2 is basically Java 8. So I'll be going about installing Java 8 for that, and we'll be downloading Spark as well. So wget is used to download it from a particular server, and here's the official server link for picking up Spark 2.4.4. So as soon as I hit that, our Google Colab will go on downloading Spark and uploading in its file section as well. And this will take a minute, so we'll just continue as soon as we're done with the download. So that took about 20 seconds, guys. So that was pretty quick. And as soon as you download it, it is in a zip format, right? So it's in a TGZ format. So to go about executing this, we need to first of all unzip it, right? So we will use this command called darxf, where we are unzipping it in a format where Google Colab understands what is present inside our our Spark zip file. So after this, we have to install something called as Find Spark. Can you guys quickly guess what Find Spark is? Probably take a second to figure out what Find Spark is. Think about it. I mean, if you can't figure it out, it's fine. So basically, to keep your Spark instance to be portable, we make use of Find Spark at the end of the day, guys. So this is a very tiny module, so this should be I'm guessing installed in 5 seconds, and that's done. Again, you need to set up a couple of environment variables. We have to set up Java home. We need to set up the environment variable Spark home. So this is the code to go about doing that, and as soon as I hit play, that's done. So let us go about creating our first Spark session, guys. So we'll be importing Find Spark, or to go about starting your Spark session using findspark.init method, and then we'll be importing PySpark.sql. So we'll be including the SQL module from the particular Spark session, and at this we're just telling that we'll have only one local instance where you're working with it. So again, at this point of time, we're doing nothing but just creating an empty session for us. But you need to know that we have further code to check as well. So I cannot just go about executing further code because Spark session is already running right now in Colab. So let me quickly stop our session so we can pretty much rerun it again. Next up, we need to install PySpark. So we've installed Spark now. Let's quickly install PySpark. So this should take about half a minute, which is what I assume. Let's quickly import PySpark again, begin a new session. Let's go about creating our Spark context, right? So from PySpark, we're importing Spark configuration. Again, from the same module, we're importing Spark context as well. We're setting a variable, configuration is equal to Spark config. Conf.set master is local. We're telling it that this is the only local instance which will run. You can have any application name that you want, and here we just call it Spark Basics, guys. You have SE. SE is again our Spark context variable, where it's pretty much simple, guys. So you use this code, and this code is, our standard, which is set to pretty much to go about creating your Spark context of your own. So let me run it again. It should take less than 10 seconds to go about running it. Here is what we were discussing in the PPT. We're defining a modular function where we're importing numpy and we're returning the modulus of that. So again, RDD is equal to sc.parallelize range of 1000, mapping it using the take function. I know that you guys are not familiar with any of these right now, but then to give you a quick example, this is how it works, guys. So basically, it is like a list of all of the elements. Again, it has a structured data type. It forms the native of Spark. And don't worry, I have lots of examples that I'll be showing you, a lot of functions, a lot of operations that I'll be walking you through when it comes to RDDs as well, which is actually the next section that we'll be checking out. I just wanted to get you familiar with Google Colab in case you chose to use another Python IDE for the previous modules, and I just wanted to show you how you're what you need to go about setting up your PySpark job, guys. So what are Spark RDDs, guys? So I've already told you Spark RDDs pretty much stand for resilient distributed data sets. But at the end of the day, how is it? Why do we need it? What is Spark? We'll be just checking it out in this particular module, guys. So this module is basically all about RDDs, and we really need to know what they are, why we need it, and all that, right? So RDDs are immutable. They are they are separate, split, structured partitions of data. So basically, data, records, collections all mean the same. And they can be, how can they be created? As basically you can have a couple of functions work on it. I'll be walking you through the functions as well. We have map, we have filter, we have group by function, load, and loads of functions. So when you have all of these operations done and you have certain things which are done to your data, well, most of it is you need to save your data after after you do certain operations on it, right? So to have a certain stable storage media, the media can be HDFS as well, and so after the transformations that's being done, you need a place to store it. So the transformation being worked on that particular data, guys, that is what RTDs are mainly used for. So there's a couple of things that I need to walk you. Very important things is pretty much with to start with. It is again, the first thing is in-memory computation. RDDs support lazy evaluations, fault tolerance, very good immutability. Again, as I've mentioned, partitioning, very good persistence, and coarse-grained operations as well. So what are RDDs again? RDDs are the main logical data unit in Spark. This is the most important aspect of this module. They are again a distributed collection of objects, which are again, they can be stored in the memory, they can be stored in the disks, not just of one single machine, but they can be stored in the disks of multiple machines. And one single RDD can be divided into multiple logical partitions, and these partitions can be stored, these can be processed on all of the machines in a cluster as well. So again, yeah, RDDs, they can be caged, they can be used again and again, no matter how many times that you require for any of your future transformations. I mean, these are small files, so at the end of the day, you can keep caching them and reusing them. And coming to lazy evaluation, do you guys know what lazy evaluation is? If you do not, then again, as we've already been doing, take a quick guess of what lazy evaluation means, guys. So I hope you could guess it. It's basically, you have variables in your programs which are always bound to your certain data, and they'll be executing it, right? It's to have the evaluation separated from the data until the results are obtained, is basically what lazy evaluation means. To delay your evaluation. So let's say you have an expression, you'll pretty much be delaying the evaluation of it until that is required. So that is the very simple explanation of what lazy evaluation is. And again, RDDs can support lazy evaluation, and it can support transformations and actions on these RDDs as well. So here's a quick workflow of how an RDD works. So we have RDDs, we have 1 and 2, which again club into single simple units. And then RDDs are like arrays, right? So they're pretty much structured data. So this structured data gets converted into graphs. DAG is directed acyclic graphs. And with a directed acyclic graph, what usually happens is data flows from one node to another in a structured manner, where data can jump back and forth, and each node is connected to another node which is ahead of it. So basically what I want you guys to figure out at this point of time is to know that the RDDs goes from looking like arrays and a lot of numbers, and it basically goes into a graph where our Spark unit can understand what's going on. So after our DAG scheduler finishes its work, where it assembles it, orders it, and stores it, so this is next passed on to our cluster manager. A cluster manager will figure out where to pull the data from, right? So it can be EC2, it can be via Kubernetes. You can pull the data from a lot of places. So our cluster manager again is used for this. So all of the tasks set from our RDD. So consider each individual RDD operation to be a task, right? So this entire task set is pretty much pushed onto our task scheduler, where the task scheduler will figure out when to execute what, and how long to allocate a resource for that particular task, and so on. And so all of this data is pushed to the executor, and our executor will go about executing and giving us the required output that we eventually require, guys. So why would we require RDDs, guys? Think about it. So just to answer that question is the next part of this module. We need to find out what are the stop gaps in the existing methodologies that lead us there, right? So firstly, I have in-disk computation, guys. So before the existence of RDDs, what used to happen was we had, again, ton loads of data back in the day as well. But all these data were being processed in a hard disk, in a spinning, slow hard disk. So we already know that in-memory computation can be done, which is already supported. Obviously, executing something in your RAM on your cache is 100,000 times faster than what it's done on your hard disk. So with in-disk computation, again, we needed something to go about stepping up our game, and we needed in-memory computation basically. So again, with in-disk computation, you're going to be using a lot of memory to store, and at the end of the day, if that is slow, it really is a turn off, right? So next we have job execution. So basically, whatever was existing, right? So consider MapReduce basically. So MapReduce needs to store some of its data. It needs to have an intermediate storage space, which again we called it HDFS. So it needs a place to store all the intermediate data to access it, to pick it up again. With the job execution, another important point is that it makes so overall computation of your jobs are really slow. So probably we can imagine and we can handle slow execution if it's one job, 10 jobs, and it takes about 5-10 minutes. But if a 10-minute job was taking about 35-40 hours, then that would really slow down things, right? So again, overall, it slows down your input-output operations, serialization operations, replication operations, and so on. With parallel processing, again, when we didn't have Spark, most of the data processing were not done in parallel, first of all. And even if an application supported parallel processing, it was not as efficient as that, guys. So we know how the RDDs are solving the problem for us. Well, mainly RDDs have, again, as I've mentioned, they have a huge capacity, huge capability to handle various volumes of data. So how does this do it? Well, basically it processes them all parallelly. It has multiple logical partitions where it can access, work on each of the partitions, and then save it later, guys. So you can go about creating an RDD whenever you want, but it's only executed whenever they are needed. So you can go on bunching up, creating tens and hundreds of RDDs that you want, and since Spark supports lazy evaluation, it'll only be picked up whenever it is needed, guys. So let's quickly check out some facts to go about explaining why RDDs are better than what's existing today. And the first important point I want you guys to note is that it supports enhanced distributed computing, guys. So distributed computing in this day, in terms of big data, is again a big boon, right? So again, Spark RDDs are useful for distributed computing, which involves processing lots and lots of data over lots and lots of computers with respect to lots and lots of jobs, right? So having this distributed computing capability is a big thing, guys. And secondly, partitioning. Well, RDDs again are partitioned. So basically, by partition, what we mean is, in simple terms, it is basically split into a couple of logical partitions, guys. And the partition data is distributed across all the nodes that are present in the cluster as well. So that is again a very important fact of why RDDs are better. And thirdly, location stickiness, guys. So basically, RDDs can define their own preference, so they can have their own location to where they have to stick to the partitions and where they need to be present for the data requirement procedures. So again, location stickiness is again another very important reason of why RDDs are required. Next up, let's quickly jump in to find out what are the features of Spark RDDs, guys. So as we already talked about this, as I already mentioned this, the first major important thing of Spark RDDs is in-memory computation, guys. So, and any RDD for that instance and all the data that are present there, it can be pretty much pushed onto your memory, and you can have it stay in that memory for as long as possible. And this is, I've put it first because this has to be the most important feature of Spark RDDs, guys. And secondly, with respect to immutability, you need to know at this point of time is that an RDD pretty much cannot be changed once it is created, guys. So that is what immutable means. And sure, you can perform certain transformations on it, and it can only be transformed, but it cannot be changed on the whole. So RDDs are immutable, guys. Lazy evaluation, again, the data, it's not available or transformed until something is executed where it triggers the requirement. So you can code in 10-15 RDDs and you can just leave it there. It will only be picked up when it is needed, right? So again, supporting lazy evaluation is again another big advantage of this. Coming to cacheability, guys, this is again another very important feature of Spark RDDs, where our cache storage, it stores all of the intermediate RDD results just in the memory. So nothing is being pushed to your hard disk or local storage. And the biggest advantage here with RDDs is that the default storage for its cache is in memory, guys. So this ensures higher efficiency, better speeds of data access, and all of that. And the next important thing is parallel data processing, guys. So to process data sequentially is surely an advantage. But to go about processing your data parallelly, side by side, is something which takes, which requires a lot of muscle. So again, we can be very happy and satisfied with RDDs because RDDs can process the data in parallel for us. And lastly, the another important feature of Spark RDDs is that it can have types, guys. So it is a typed configuration where your RDDs can be of the type integer, it can be of the type long, it can be a float, and this again ensures better readability. It is more concise. It gives you that feeling of tailor make where you can have your data which is in perfect condition, where as soon as you glance at it if it's an integer coded data, if it's data with large numbers using long, or if it's a decimal number which has float and whatnot, guys. Next up on this module, we need to check out the ways the ways which is basically used to create RDDs in PySpark, guys. Again, that's the basically that's the symbol of collab that you see on the right in yellow. And we've already checked out how we can create RDDs in that simple example I showed you, right? So we'll be importing Spark configuration, we'll be importing our Spark context. Or to go on about creating a Spark context, we'll be creating a conf object, guys. So basically this provides the entire configurations for our Spark application. You'll be setting the application name, you'll be setting the master node as well. In this in the example that you see, it is local because there'll be only one instance in this particular example that I'll show. And so we'll be defining the app name, the master URL as well. Master URL is local in this case, and we'll be using SC. SC is nothing but an object which is derived from our Spark context, guys. So we can go about doing another quick set of operations as well. So we can create an RDD using a simple list. So we have already walked you through list in module 2. So just quickly revise the concepts of lists. So here we have a variable values, and we have 5 elements in a list, and then we're performing this operation called sc.parallelize, and we'll be passing the values. We'll be passing the values and creating the RDD using that, guys. So sc.parallelize is an unfamiliar syntax for you, right? So sc.parallelize is an unfamiliar syntax at this point of time. So the parallelize method, basically when you're applying it on a collection, right? So in our case, the list is the collection. So when you're going about doing that, basically a new RDD is created for us, and all of the elements that are they are copied into this particular RDD. So parallelize will pretty much go about creating a new RDD as well, and the syntax to go about doing is parallelize and passing it a collection, guys. And to print an RDD value, we usually use the take function, guys. So rdd.take of 5 will pretty much print the 5 items which are present in our collection. And moving on, there's a couple of things I'll be showing you practically as well. So to upload a file to Google Colab, we have this particular syntax from google.colab, import the files, and then we'll be pushing it into a variable, uploaded is equal to files.upload. Again, that is a GUI. Again, I'll be walking you through that in a second. And, we can go about initializing an RDD using a text file, guys. So if we have a particular text file where we're, doing something, or we have a lot of data in the text file where you want your RDD to pick up the data in the text file, sure, you can do that as well. And we can go about printing the text from the RDD as well. So let's quickly jump into Colab and we can check out the next set of demos, guys. So again, here's the demo that we're talking about. Values is equal to 1 2 3 4 5. It's a quick list for us. Parallelize creates our RDD, and as soon as I hit take, we'll have the output of it, guys. So uploading files to Colab, again, as soon as I run this, just see what happens. So it will allow us, it's still running, so it's still waiting for me to put up a file. Let me quickly, jump to our desktop. We have a Spark file which is ready. It's a text file, basically, nothing important. So basically I have, I have some gibberish written in there for this example, guys. So loading a text file is again pretty simple. sc.text file of spark.txt. The location here we're giving spark.txt because, inside the files we already have it. So there is no other no other path where we have to provide it. So it is just files in case of Colab, guys. So as soon as I go about running this, it will pick it up. And as soon as I hit rdd.collect, which is basically used to print the RDD data, so it will say Apache Spark with Python is PySpark. So this data our RDD has picked up because of what I have put in the text file, guys. So it is as as simple and straightforward as that. Moving on, the next concept that we'll be checking out is something called as persistence and caching, guys. So to begin, we already know that RDDs are support lazy evaluation, right? So you can go about using the same RDD any number of time you want, and it'll go on recomputing it as well. So, this goes on for a while. Sure, for small amount of data, it won't have a major damage. But for large, huge data sets, which are worth terabytes, say, to recompute it every single time, I don't think it is very efficient, right? So to go on avoiding this recomputation on a single RDD multiple times, you can have your Spark to persist the data. So persist the data will pretty much store it in its partition and hold it there. So if the node that pretty much computes the RDD and pushes it to the partition, and if the node has a data, let's say if there is a node which has data persisting on it and it fails, so sure, Spark will again recompute all of the lost partitions of the data when it's required. So that is the keyword here, when it's required, right? Not all the time. So again, sure, RDD. So can you only persist? No. With RDDs, again, they come with a method which is called as unpersist. So unpersist will again let us, remove all this data manually from the cache. So let us say you do not require it and, you require your cache storage. Again, cache is again, a small amount of data, right? You cannot push everything on the cache and rather have it stagnant there. So basically you can use the unpersist method that, you can go about removing all the data, RDD data from the cache, guys. So here's a quick persistence level chart I have for you guys. So with persistence level, you need to know that, you can perform, this is basically to give the user flexibility, guys. So with the memory only level, you'll be pushing all your RDDs onto your cache directly. That's why the space used is high. The CPU time is low because the data is accessed faster. It is always pushed in the memory and none is on the disk. So again, it stores an RDD as a Java object basically. And so what happens if your cache is already full and it doesn't support? Most of it is saved into the cache, and the other part which is not cached will basically be recomputed when needed, guys. So again, we have memory only, sir. We have memory and disk. We have memory and disk, sir, and we have disk only, guys. So at this point of time, I would just recommend you pause this particular section to glance through of the levels, guys. So there is, you can have high CPU time as well, which is, not efficient if you push everything on your disk only, and none of it is pushed to the cache. None of the intermediate storage is pushed to the cache, and all of your data are on the disk as well. So this again is inefficient, right? So quickly, pause the screen and have a look at this persistence chart, guys. So coming to caching, guys, we already know that caching data is very important, and when your data is being accessed repeatedly, right? So again, it is very important to go on caching it. We call it a hot data set because you might require it at every single point of execution, say in an iterative algorithm and whatnot. And cache is fault tolerant, as we've already discussed. And let us quickly go back to an example, and we can check out the example where you can have a data set and you can pretty much have it caged, guys. So let me quickly jump into Google Colab, and we can work out with it. So coming to persistence, as we already have it with persist, it is going to hold it in the cache, and it is going to tell you where it is holding it, guys. So this is again a very important readability aspect of Spark as well. And coming to caching, as soon as we go ahead and hit spark.txt, again spark.txt is the file which we imported a couple of minutes ago. So with that, again text file.cache, so basically text file.cache is used to hold it there. And to basically at the end of the day, as a developer, as a programmer, to know that your data is fault tolerant and it will be there if something messes up is something important, guys. So now that we're done with that, let's quickly jump into operations that we can perform on RDDs, guys. There's a lot of operations that you can eventually perform, but then there's two main important types of operations that you can perform. So the first one is called as a transformation. Think about it, right? So RDDs are immutable, as we've already discussed. So to work around this, we need something called as a transformation. So the transformation will basically return a new RDD, guys. So a lot of emphasis on the word new, guys. Since it's immutable, then creating a new RDD is, it's inexplicable. So creating a new RDD is a great requirement, guys. Again, what an action will do is basically it will return one singular value to us, and that will make our lives a lot simple, guys. So you will basically figure it out when you're getting your hands dirty with a lot of code. And without further ado, let's quickly check out RDD transformations, guys. So again, transformations, as the rest of RDD concepts, are all lazy operations that are basically performed on one RDD unit. And doing this will eventually lead to a transformation, will lead to creating one or more new RDDs as well. And how will it work? Well, here it is. RDD transformation, pretty much, it will return a single pointer which is created to the new RDD. So our application needs to know where the new data is going, right? So basically pointer is used to memory map that. So our transformation will basically return a pointer to the new RDD, and it will allow us to create the dependency which is required in between each of these RDDs. Because let's say you have a couple of RDDs and each has a function to do something. Each has a unique function to it, and then to go about letting the RDDs talk to each other, calculating the data, having it stored in one common place, and all of that, right? So it's usually a parent RDD, and under the parent RDD we have what we call pointer dependency towards the child RDDs, and we work on with it. But at this point of time, let me not bombard you with a lot of in-depth details. All you have to know at this point of time is pretty much there is the dependency which exists in between each RDD, guys. Again, Spark is lazy, right? So by lazy, what we mean is lazy evaluation. So nothing will get executed unless you actually go about making some transformation or having an action that will actually create a trigger. So the trigger is basically what starts the operations here. So you can have job creation and execution there as well. So RDD transformation is transformation is basically not a set of data. You might be wondering if it's a set of data at this point of time. Well, it is not. It is a step in a particular program. It can be the only step, or it can be one among many steps. And so how the transformation works is it basically tells Spark how to get the data and what to do with it, guys. So couple of transformations that you can that we'll be walking you through with is basically map. We'll be checking out flat map. We can check out filter. We can check out map partitions with index. We can check out samples, union, intersection, all of these, guys. So without further ado, let's quickly check out each of these operations, guys. So the first transformation we'll be looking at is the map, guys. So what map in simple terms does is basically it passes every single element through a function. So think of mapping in literal terms, right? So let's quickly jump into code where it will be better to understand with code, guys. So again, we have a list. This is basically all strings: Spark, RDD, example, sample, another example. Say. So as soon as we use x.map and we pass a lambda function through it, so what basically happens is it lets us map it into key value pairs that you can you can go about seeing here. So Spark is mapped with one, and RDD is mapped with one, sample one, example one, and all of that. So our lambda function is pretty much used to perform the mapping here. So again, this is the code that we just walked you through. So you can pretty much map the key value pairs to be anything that you want, and this is the it is used to add a little more structure to our data, guys. So next we have flat map, guys. So flat map, what I want you guys to know at this point of time, it is pretty much exactly like mapped, but then you can have your values to be mapped from any, say, from 0 to any number of output items that you want. Why would you do this? Because let's say you have a function that should return multiple number of outputs, right? So we already know that majority of our functions will only return one output. But let's say we require a function which requires more than one output. So let's say you require a sequence. So in that in that particular case, we will require the flat map, guys. So again, we have sc.parallelize. We're basically creating three elements, 2, 3, and 4. And we are passing it around to our rdd.flatmap lambda function. Range is 1 to x. Dot collect again is added instead of doing separately. So basically here we have separated out y dot collect, and here you can go about adding it there as well. So this again is pretty much creating instances and copying the values for us. So as you can check out 1 1 1 2 2 and 3, guys. So flat mapping, again, you wouldn't use it directly, but then you can go on a mapping to multiple elements that you want. You'll not be using it practically, but then hey, it's good enough. It's good to know, right? And next up we have filter, guys. So filter again, it returns a collection of elements which is you're filtering based on something, right? So think about filter in general as well. So you're filtering something based on name, based on ID, based on your roll number or whatever, right? So again, filtering here works the same way as well. So you have a collection. In our case, most of it is lists, and we'll provide a condition to it saying if this condition is valid, just collect all those elements for us. So coming to filter again, we have 1, 2, 3, 4, 5. If any of these individual elements, when you perform the modulo operation 2, if the remainder is basically 0, then we go about collecting it, guys. So we're going to divide 1 by 2, you will get a reminder, so that's not picked. You divide 2 by 2, remainder is 0, yes, pick that. You divide 3 by 2, you will not get, you will have a reminder of 1, right? So that will not get picked. 4 divides 2 with a reminder of 0, yes. 5 doesn't. So go about doing it, you'll get 2, 4. If you can, put in a 6 here, then you will pretty much get 2, 4, 6 as well. So it's as simple as that, guys. Next up, we have the sample operation. So sample, pretty much the process of sampling is where we small amount of data which either requires replacement or which doesn't require replacement, right? So having a sample doesn't have to have any ordered values, right? So you can have any random number generator to give you certain random data as well. So with the sample operation, we can have 3 parameters, guys. So this method supports 3 main parameters. The first one is with replacement. So with replacement is basically say sampling a certain element multiple number of times, right? So when you're sampling it out every single time, then you can have it replaced as well. The next up is the fraction. Basically with fraction, you go about making the size of your sample so as a tiny snippet or as a fraction of what your RDD's entire size is. And you can do this without replacement of data as well. And next we have seed. With the parameter seed, what we basically do is, it acts as a seed for our random number generator. Where we'll have a number being generated for us. So again, we're creating a number of range to 9, and it will pretty much go about generating a sample data for us, and you can work with that as well, guys. So to check out another example out here, we can check out another different range of data, but at this point of time, just quickly pause the screen, take a look at the code, and we'll be jumping to Google Colab, guys. So we're in Google Colab, and I just executed the second piece of code. So we're just creating sample data, which is from 0 to 8, and at the end of the day, we're collecting the simple sample data as well. And the next important operation that we should look at is the union operation, guys. So basically, union of two RDDs is basically concatenating and mixing all those elements. And yes, union does support repeated elements from most of our RDDs, guys. So let's quickly jump into Colab and execute it. So we have 1 to 9 on our first parallel, and then we have another variable called as par. We're going to take an object of it from 5 to 15. So as soon as you perform the union operation on this and collect it, it is going to pretty much merge everything into one collection, and that is basically the output that you're greeted with, guys. So the next operation is intersection. Again, similar to union, but then it is the literal intersection, right? So whatever is in common in between both of these RDDs is what we'll be getting out of it. So quickly executing this piece of code from range of 1 to 9 and 5 to 15 in the numbers being generated here. 5, 6, 7, 8 are what is common between 1 to 9 and 5 to 15, right? So that's exactly what's printed. So the intersection is pretty much the common elements in both the data sets, and it's it's as simple as that, guys. Next we have distinct. Well, with distinct, basically we are transforming, creating a new RDD with all the distinct elements, right? So as I've already mentioned, it supports repeated elements, but let's say we do not require the repeat elements, right? So sometimes we require this hard coding where we require only distinct elements from it. So to go about doing it, basically all we do is it is exactly the same as our old operation, but again here we're doing a union operation. We'll just be adding the dot distinct method, guys. So dot distinct will eventually tell the interpreter to just give us distinct output and to filter out all of the repeated elements, guys. So another important thing that you can do with RDDs is basically to sort it using something, guys. So you can go on mapping something to another key that we've already seen, but what if you have to go about sorting this with respect to any of your personal any requirements, right? So here we have a sort by function, and this pretty much supports sorting in the ascending order, guys. So we have random numbers out here, 5, 7, 1, 3, 2, 1. As you can already see, they are not ordered in any fashion, but as soon as I go ahead and run this, you can check out that it's ordered, right? So it's 1, 1, 2, 3, 5, 7. So if we go about adding 10 here, 10 will remain in that last slot because it is the highest number. So again, after it's mapped, can we go on sorting it as we've already seen in the slides? Yes, we can. So this will be mapped again in the ascending order. So whatever is mapped for 1, Z comes first. Whatever is mapped for L comes next. Then H comes because it is the next 10, and lastly we'll get A, which is 26. So sort by is pretty much as simple as that, guys. So let's quickly check out the next one. The next is something what we call as map partitions. And map partition is the a simple alternative when you have to use map and for each, guys. So map partitions are pretty much called only once for every partition. But in the case, if you remember, in the case of map, where what used to happen is we used to, basically it was an iteration, right? So we used to call it every single time for every single element of every single collection. So to pretty much bring up our efficiency, what we do with map partition is we call it only once. So we've defined our function f, and we have a variable called iterator, and we have something called as yield sum iterator here, guys. So what happens here is you just pick it up once, you pick up the data once, you iterate through it once, rather than just picking up single data for every single RDD. And so, but then that particular instance, what we saw, it was not indexed, so you do not know how you can go about pulling the data and what the data actually does. So to get a quick idea of how you can pull up the data with indexing it, we have map partitions with index, guys. So it's basically a single term, but then I've just split it out in the title to just get better readability. So what map partitions with index does is it returns a brand new RDD for us by applying a function on each partition of the RDD while tracking the index of the original partition. So we need to find out what the original partition's index is, and then we will go on keeping a track of it, guys. So we have 1, 2, 3, 4 and 4. As soon as instead of just throwing in our iterator variable, we have something called a split index that we'll be pushing onto our function. And as you can see, instead of just using rdd.map partitions and collecting it later, we're pretty much going about map partitions with index, and then we're yielding the sum operation of it, guys. Again, you will not be using all of these operations on transformations on your day-to-day basis, but then it's really good to know that you have access to all of these and you can go on using it, guys. So next up we have group by, guys. So if you guys are familiar with SQL programming, the group by here pretty much works the same way as well. So what we basically do is we return a brand new RDD as we've been doing with all the transformations. We do this by grouping objects in the already existing RDD, and we'll be using a grouping key to know what we are grouping it by. So let's quickly jump into the code where we can check out group by, guys. So again, we have a collection 1 1 2 2 3 5 8. So rdd.group by is what we'll be using. So we're gonna group by the values if it performs and validates the module of 2, and we'll be collecting that, guys. And later we're sorting it as well. So as soon as we go about executing this, we get 0 2 8. That's valid. We get 1 1 3 5 as well. So basically you're grouping it with respect to an order. You're getting a key value out of it, and then you're sorting the key, guys. It is really simple. So the next thing is something called as key by. So what a key by does is basically it changes the key of the RDD element that we have been working on for a while now, and it does this using our given key object, guys. So with the key objects, you can already check out the code. So we are basically doing an exponential operation, x multiplied with x, and we're basically having a value from the range of 0 to 5 with us, and we're performing the list operation on it with y. And lastly, again, we don't know yet what the zip operations means, which is exactly what we'll be checking out next. But what you need to know is basically we'll have a key, and you can have your individual collection items of the data arranged with respect to the key, guys. So what is zip? So the zip operation, it is used to join the two RDDs by combining a certain part of each other, right? So think of it as a literal zip locking with each other, right? So you have one part of one thing, one part of the module talking to another one. So it is pretty much something like that here as well. So basically what we do is we return an RDD formed from this list, and we create another collection by combining all of these elements that we have obtained in pairs. So we obtain a pair from one RDD, we obtain a pair from another RDD called y, and you can check out the iterative example on the screen as well. So we'll be picking out say A from RDD X with the data values 1 and 2. We'll be merging it with the data values of Y, which has the values of 4 and 1, right? It's pretty much as simple as that. So this will work when we have both of the RDDs of the same size, right? So what if one of the collections has a bigger size? So then what will happen, it'll map all our common elements, but whatever is in excess, that is pretty much ignored, guys. So let's quickly check out our zip function. So we have the range 0 to 5, 1000 to 1005. We'll be zipping our y with respect to x, and we're going to be collecting. So 0, 1000, 1, 1000, 1, 2002, 3003, 4004. Perfect. So next again, we'll be checking out our zip with index, guys. Again, it's a single word, zip with index, but for readability, I've just pushed it out separately. So what we do here is pretty much we'll create a new RDD. Again, we'll be pairing all of our elements that are in our list already. So whatever lists are present for us, we'll be checking out all the elements that are present there, and we'll be pairing it with their index as well. So you need to know that with Python, again with Spark as well, with PySpark, and all the indices start with 0, guys. So since we're just adding an index for it, all you can do is pretty much A, B, C, D. The output we should give it is 0 1 2 3, guys. So A will be mapped to 0, B will be mapped to 1, C will be mapped to 2, and the index of D is mapped to 3. Pretty simple, right? So next we have the repartition transformation. So repartition, if you've ever played around with installing Windows, Linux or something, then you would have been familiar with what repartitioning a storage medium means. So basically you'll be changing the number of partitions, guys. So it is either it is used to increase or decrease the number of partitions in an RDD. In our case, so how does it work in the back end? Well, all it does is pretty much it does an entire shuffle of all of the data, and it creates new partitions where our data can sit in a fashion manner, and all these data, all the partitions are distributed evenly as well, guys. So let's quickly jump into Google Colab and let's analyze. So the data we have is 1, 2, 3, 4, 5, 6, 7, and the second data set is 4. We're sorting it. We're using rdd.glom to pretty much go about with our repartitioning. So the output we should expect is 1, second element to be 2, 3, third element to be 4, 5, and the fourth element to be 6, 7. Perfect, guys. So to find out the length of this, again, coming back to my presentation, again, to find out the length of this, you can pretty much use the repartition.glom. So repartition of 2.glom.collect is again giving our outputs. As soon as I go ahead and run this, it is going to tell us we're basically working with 2 RDDs, and 2 partitions have been created where the data is being stored uniformly, guys. So it's pretty simple. Next we have Coalesce. With Coalesce, the practical part of Coalesce is think about it, right? So you will have thousands of partitions when you're working with a huge data set. Coalesce is again used to combine, it is used to unite a couple of partitions where the data might be similar, or the data is not similar, you just want to bring it under one RDD, then Coalesce is pretty much your friend, guys. So we have 2 data sets here, 1, 2, 3, 4, 5, and 3. So as soon as we pretty much use .glom.connect with Coalesce, as you can already check out, we have one single entity which is giving us the data, and the data is being merged and united into one, guys. Just a quick info, in case if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. The link is given in the description box below, so make sure to check it out. And on that note, let's get back to the class. Here is another example of how Coalesce works. With Coalesce, again, you can already check it out that we've split up the second element as we've used in Glom in the first example, and in the second example we've pretty much gone about coalescing it and bringing it into one single unity, guys. One single entity, sorry. So next, so what is repartition? What is Glom with respect to repartition? What does Coalesce have in difference to each other? With Coalesce, you need to know that we'll be using the existing partitions which are already present, guys. So this is basically used to, it is used to keep the data which is being shuffled into a certain minimum extent. But with repartitions, it always does a full shuffle of all your data, and it creates brand new partitions for every single collection of every single RDD, right? Again, with Coalesce, results basically in every single partitions, they are stored with different amount of data, right? So not every single data element is of the same size. With repartition, again, repartition tries to pretty much partition your data in such a way where each of the data partitions are pretty much almost equal sized. Coming to the speed of execution, Coalesce is pretty much a lot faster because first of all the shuffle is minimized, and second, it has data of its own different dimensions. So whenever data needs to be picked, honing in and hunting in on the data is really faster with respect to Coalesce than repartition, guys. So repartition is a little slower when you compare it to Coalesce, guys. So all these while we were checking out transformations with respect to RDDs, right? So next we can go about starting checking out the actions we can perform on the RDDs, guys. So we're already aware, unlike transformations, RDDs, they pretty much create another brand new collection for us. But here with respect to actions, what we actually do is we create a new value which is given back to our Spark driver program, guys. But then to start an action, it needs a trigger. So actions have to be triggered with either a previously constructed RDD or another data entry point, guys. So with respect to the RDD functions, there is a couple of functions that we'll be checking out, and there's the reduced functions. There's first, there's take order, take count, collect for each min max functions, standard deviation functions, sum, mean, variance, and all these operations, guys. So let's quickly start out with reduce, guys. So with reduce, what it basically does is it brings everything, all the collections of a data set, and we basically run all of these through a function of our choice. So as soon as we go ahead and let me quickly jump into Colab where we can go on checking reduced. So with it, the syntax is again pretty simple, guys. So for every method, every action, every transformation, we have a dot method which pretty much corresponds to it, and we'll be following the function that it needs to be passed through is basically the parameter that is supposed to have for the reduce function. So as soon as we run this, it is going to add all of the elements that are present in our function, guys. So just passing it through a simple function is what we're doing out here. So here is another simple example that we'll be pulling for all the values of in the range from 2 to 10, and so all these value here as well are being added together, and we're being given the output, and we're running a lambda function as well, like we've been doing for a while now. So if you guys are having some quick time running, remembering lambda functions, I suggest you quickly jump into our previous module to get a quick rundown of what the actual lambda function does, guys. The next action that we will be checking out is the first, guys. So first, again, if you can guess, it pretty much gives us the first element in our collection, right? So as soon as I go ahead and hit this, I get 2 3 4. The first element has to be printed. So if I do it 1 2 3 4 and run dot first on it, it is going to give us 1. So it is as simple as that, guys. So parallelize will be inputting our collection, and we'll be running the dot first method on it. The next action is take ordered, guys. So basically what we do here is we'll be returning an array with a certain set of ordered values for the RDD, guys. So consider the example on your screen. We pretty much have input 1539402, and we'll be taking elements in the ordered value of, we need 5. So basically what we're trying to tell you here is we need 5 values, and we'll be taking it in the ordered sense, guys. So the first 5 values in the ordered sense will be 0 1 2 3 4 again. So again, as you can check it out, we have 0 1 2 3 4, because these are the first 5 ordered elements that we are outputting from the RDD that is present, guys. So next we have take. Take again, it pretty much picks up your value, but it does it without an order. So whatever order your RDD has been input in, or the collection that you've input in, is what it is exactly considering here, guys. So we have 1 5 3 9 4 0 2, etc. So this here will be picking up the first 5 elements in the order of their occurrence. So as you can check out, 15394 is being picked up, but here we are picking it up in the ordered way. So that's the difference between take ordered and take, guys. So next we have count. Count, I guess you can already guess, right? So it pretty much tells us the number of elements that are presented that are present in an RDD. So as soon as we go ahead and hit count, let's count manually, right? First, 1 2 3 4 5 6 7. So we have 7 elements. As soon as we run dot count on this, it should pretty much tell us that there are 7 elements present. Let's go ahead and add another one just for the sake of it, and it says 8. So the dot count method pretty much gives us the number of elements which are present in that particular RDD, guys. And next we have the collect action. So with collect action, what we're basically trying to do is we're trying to get all of our elements as an array, guys. So at this point of time, with certain transformations, we were creating brand new RDDs, but with actions, we're not doing that, right? So with actions, let's say if our driver program requires an array, it requires an entire structured data input. Collect pretty much does that, which we've been using and seeing for a while, right? So with collect, I mean, we're using collect for a while here right now. So pretty much I'm sure you guys could have guessed it. So the collect action pretty much just pulls it out and gives us the array output that we've been seeing from our first section. And again, here is another example as well. So it's pretty much just another different just a different collection of elements out here that we're pulling it out. But what we're doing with respect to the second one and the first one is, if you guys can see clearly that we have the distinct the distinct method which is being present here. So we have GNU, cat, rat, dog, GNU. So GNU was repeated twice, rat was repeated twice, right? So that is pretty much being avoided just because we're we're making use of the distinct method, guys.
So collect is very simple, and next we have save as text file. So basically, let us say you want all the data which is stored in your RDD and you want to push it as a text file. So you pretty much, I'm sorry, if you want to pull it as a text file. So if the RDD's data set has to be presented as a text file to you and it has to be stored somewhere in your local file system or your HDFS, then pretty much you'll be going about doing this, guys. So with the save as text file, so pretty much we'll have a sample data which is generated for us, and as soon as I hit this, so if you're using a Linux or a virtual machine, this is usually how the data goes about with the path. So slash user slash bin slash my data a1 is the text file where the random data is stored, guys. So again, we can have instead of random data, we can just pretty much go about giving our own data and then pretty much having it save as a sample file for us as well. So since we're doing this on a Google Colab on a Jupyter Notebook, the files which are pretty much output are saved online. But if you're doing this on a local machine, then you have to give the full path of the file that you need to put. So let's say you want it in your desktop, you just cannot save desktop. You have to just go about doing C drive users, your username, and then desktop and the file name, right? So one important thing that you need to know is with Windows or with Linux, the extension is very important, guys. So I have had a couple of learners come to me with an error. So the file doesn't pretty much open because your native operating system such as Windows or Linux, it does not understand the the type of file which is being processed. So that is again another important thing which I pretty much wanted to tell you guys about. And jumping back to the slides, we have the next one is for each, guys. So with for each, again, the practical literal use of for each is where we are passing every single element into a function of our choice, right? So here we have defined a function called it f, where the variable is x. So what the function has to do for us is all it has to do is print. So we have defined the function, we're printing it, and then all we're running is this. We're running this RDD, and we're using the for each method to go on printing that out, guys. So let's quickly check it out. Basically, we're just printing each element and we're running it across the for each loop, guys. So next we have something called as the for each partition. Well, with respect to the for each partition, what we're trying to do is we're executing every single function for every single partition. So the access to all of our data elements that are contained in every single partition is, how can we go about moving with respect to every single element is basically we'll be using as an iterator as an argument, guys. So we'll be pushing an iterator to tell us how we can step across each single element and how we can go about printing it, guys. So for each partition is very simple. So we have a function which does the operation where we're running through each of the instances and we're printing x, and we have 1 2 3 4 5, which is our data elements. As soon as we go ahead and collect all the partitional elements here, so pretty much we'll be greeted with the same output of 1 2 3 4 5 as well. And now coming to a little bit of mathematical operations, we'll check out what min, max, sum, mean, variance, and standard deviation all mean. So Spark RDDs again support actions like min, max, sum, max, variance, and all the standard deviation operations as well. So I think it's better to move to Colab and show you. So let's say we have numbers, a variable where we're generating an RDD for values from the range 1 to 100. And as soon as you go ahead and sum the values from 1 to 100, the value of 1 plus 2 plus 3, so on until 100 is pretty much 4950. And running numbers.min is going to tell us what the minimum number is here. In our case, the minimum number is 1. Next we have variance. So variance is pretty much calculated by finding out the mean of it. So mean is usually the middle element in an ordered set of elements. By ordered, I mean either in ascending or the descending order, and the variance is how much each individual value varies with respect to the mean, guys. So here in our particular case, for the values from 1 to 100, our variance is what we get is of 816, and variance usually remains constant for that particular data set, guys. So numbers.max, what is the max element that are present? So basically our range starts from 1 and goes all the way up till 100 and not 100 included, right? So the maximum number in our particular case is 99, guys. So from 0 to 99, if you have to check out the mean, then the middle element that you'll be considering is 50, right? So that is exactly what we're doing here, guys. So number.mean will pretty much give us the mean element, guys. And standard deviation is how each single element deviates with respect to the mean. So we've calculated the mean, then we need to find out how much each of the single element moves away from the mean, guys. And in this particular case, it is around 28.5. It is it is pretty much as simple as that, guys. So next up, we'll quickly check out a couple of RDD functions, guys. So we already walked through a couple of functions here, right? So we've seen what caching does. So caching pretty much stores an RDD without computing it again. With collect, we'll be returning all of the single elements. Collect count by value will pretty much return us a map with the number of time that each value occurs. Then we have distinct. It pretty much returns an RDD which contains only distinct elements and no repeated elements. In terms of filter pretty much returns the RDD containing only the elements which map to that particular filtered function, and for each basically we'll be applying one single function. In our case is f. So we'll be applying one single f to all of the individual elements of the RDDs that are being worked on, guys. And with persist, again, as you already checked out, since the storage level, if it is memory only, then all of the data, intermediate data, the caching data is just stored in memory all the time. But then we can force it to bring it to our hard disk as well. That is with the persistence level table that you need to check out, guys. So storage levels are available, and basically depending on there's a lot of things that you need to check out before using the persist operation, because at the end of the day you might require one module a lot of times, but then it's not specific to get it very quickly. So then you can have it stored on your hard disk and you wouldn't mind that extra stretch, right? So something like that. And we have another couple of functions that we already checked. We have the unpersist function where we'll be forcing it to remove the persistent blocks from our memory. We have checked out union, we've checked out intersection. Count will pretty much generate the number of elements that are present in an RDD, and sample pretty much returns the RDD of that particular fraction, guys. So next we can check out count by value. So count by value, let me quickly jump into my Colab where we can check it out. So we have 1 2 3 4 5 6 7 8, again 2 4. So we have a couple of values here for our list, right? So as soon as I go ahead and run this, so if we are counting it by value, then it is going to tell us it is an integer type which is being counted, and it tries to map our values of the RDDs for us, guys. So it is pretty simple as that. And next we have to debug string. So with our to debug string, if we have to find out where the RDD is cached or where the RDD's value are being stored, if we have to check it in the backend, we'll be pretty much using .debug string, guys. So we have a range from again 1 to 19 or 1 to 13, and we're pretty much subtracting and storing it into the RDDC. So as soon as we hit debug, so wherever these individual values are stored, let's say if we have to map it for something else, or we have to use it for some other operation in the future, or to check where it is natively stored, we'll be pretty much requiring the mapped addresses, guys. So pretty much to debug string is literally used to to debug and let us know more about it. Let us check out how we can go about working with key value pairs, guys. So what you need to know at this point of time is there are a number of ways that you can get paired RDDs in Spark, right? So pretty much that's what we've been checking out for a while now. And there are many formats that can pretty much directly return all of these paired RDDs with all of their key value data as well. But with all the regular cases that we have checked, we need to convert these regular RDDs and then we have to turn it into our paired RDDs, right? So here it is being done natively. So how can we do this? We've already checked it out. Basically, we can run the map function where a key is mapped to value. So creating a pair, which we've already checked out, guys. So rtd.map is pretty much going to assign a key value pair for all of our singular elements, and it'll create pair RDDs for us, guys. So basically here you can check it out: A1, B1, C1, D1, E1, A2, B2, C2, D2, and E2. So this is pretty much two different entities, and you can see a key element from A1 being mapped to the rest of the elements here, a key element from A2 being mapped to the rest of the elements there. And so again, here is another quick recap where we've checked out all the transformations that we've done. So reduce by key, again, it combines all the values with the same key. The syntax that you go about doing it is RDD reduce by key, and you pretty much send the function to it, which is add. And then group by key, group by works exactly how it works in SQL, as I've mentioned. It grows group bys with respect to one single key. With the map values function, it basically applies one single function to all of the values in a paired RDDs, and it does this without changing the key. With flat map values, basically, we're applying one single function that returns an iterator to each of the values, right? So for each element that is being returned, all we are trying to do is we are trying to produce a key value entry. This is being done with respect to the old key, guys. So we use this with the process what we called as tokenization, but then we'll be looking at it in the next couple of modules as well. So you can you can check it out then. And next we have the keys function, where we basically just return an RDD with the presence of the keys in it. Sort by key, where you can pretty much go about sorting all these keys and then having an RDD give you these sorted transformations as well. So subtract by key will pretty much remove all the elements with the key that is present in the other RDD, guys. So if the same key is present in the second RDD, then it pretty much removes all those elements when it is clubbing it and transforming it into the next RDD. With the join function, basically what it performs is it performs an inner join. So inner join again is another SQL concept here. So it performs an inner join between both of the RDDs, guys. With the right outer join, again it performs a join between two of the RDDs, where the key must be present in our first RDD in case of the right outer join. With the left outer join, again it performs a join where the key must be present in the right RDD or the second RDD that is being joined, guys. So with the right outer join, it must be present in the first one, the key must be present in the first one. With the left outer join, the key must be present in the second RDD, guys. And co-group, again, co-group is pretty much, it is used to group all the data from both of the RDDs where they share the same key. And next up, we'll check out something called as RDD lineage, guys. What is RDD lineage? So RDD lineage is basically a graph with all of the parent RDDs which were given before transformations, guys. So as soon as you apply a transformation, we're already familiar that another duplicate RDD is created and that RDDs are immutable and so on. So lineage pretty much graphs us out, it gives us a graph of, it gives us a DAG, directed acyclic graph of the parent RDDs of that particular transformed RDD, guys. So it creates this path, it creates a logical execution path starting from the parent RDD and going to all of the transformations which have been done, guys. So it's pretty simple. You will require this to, we've already checked it out. It's pretty much debug string to print our lineage, and it tells you the map where the memory slots are given. But then you'll only require this if you're going about debugging your application, or if something is wrong with that. To further talk about this, so basically, let's say we have an RDD graph, which is basically the result of all of the transformations that we have done. And, we have an RDD lineage graph, which is generated on that. So since we have done some transformations on it, they will actually be executed in particular order, guys. So here is to explain more about the debug string method. So basically, we have been doing rdd.toDebug from all this while. So with all of these functions that have been, let's say you've used the Cartesian method, you've used the map method, you've zipped it, you've used the union method, then you've pretty much gone using keyby, you've used another union on all of these, right? So to give you the path of execution, to give you a route that you have taken, pretty much you'll be using that again, guys. Let us check out word count using RDD concept, guys. So what is a word count program? A word count program will pretty much return the frequency of every single word that occurs in the particular file. So let's say we have an RDD that is created which basically stores a text file data, and later we have we'll perform a couple of RDD operations which will eventually give us the word count output of this, guys. So pretty much how we can go about creating an RDD using a text file, as we've already checked out. So in this particular case, we'll be uploading the file to Google Colab, and we let Google Colab take care of our file, and we'll be filtering it using our lambda function, and we'll be checking out with the length of corresponding elements to be greater than 0. We'll be splitting all the words separately, and we'll be having a flat map for us at the end of it, where we'll be splitting it based on an empty character. And lastly, we'll be using the reduce by key and sort by key, where we'll be counting the frequency of occurrence of each single word, guys. So let's quickly jump into Google Colab and let's do that. So instead of pyspark.txt, let me quickly go about doing spark.txt, because which we already have, right? So we have spark.txt. So as soon as I go ahead and create our RDD, we're picking it up, we're adding a filter to it, we are making it a flat map where we're splitting all of the individual elements, and we are actually counting the word, right? So now as soon as I go ahead and run this, pretty much all of these words have been put only once. So we have Apache Spark, with Python is PySpark. So all these are occurring once, right? So let's quickly change that. Let's have Spark here. I'm gonna give another PySpark. Probably let's do it a couple of times here. S is caps. Sorry about that. PySpark. So let me quickly save it. Come back to our Google Colab. Let's go to the part where we actually uploaded it. Or there's another simple way where you can upload files, guys. So basically to upload files, all you have to do is open this tiny tab. You have to hit upload. You can actually go on deleting this right now. Go to desktop, go to Spark, upload this. So yes, so whenever you've uploaded files, it will get deleted as soon as the runtime is recycled, guys. So now PySpark is 1, but let's create another RDD because we're picking it up from a new file. Let's filter it out again. Let's add flat map to split all the elements. Let us perform the word count and sort the words. So as soon as I go do this, it says PySpark appears 3 times. Pretty much simple, right? And then you can pretty much save this entire flat mapped output into a text file, and you can have it under the folder called as word count. So if you're using this in your local machine, you need to give the location of the folder where you'll be pretty much wanting to store the data, guys. So the next simple concept that we'll be quickly checking out is called RDD partitioning and achieving parallelism, guys. We've been talking about partitions a lot, right? So partition is nothing but a logical chunk of data, which is basically large amounts of data. And Spark manages to pretty much use all of the partitions, and it helps parallelize all of the distributed data that we have. And it has to do this with minimal network sending, right? So you need to send the data and the receive data between executors as well. So if half of your time is wasted with, just sending and pulling data, then it really doesn't make sense. So Spark has to do this efficiently as well. And it does. Well, how? Well, by default, pretty much Spark, tries to read the data into an RDD from the nodes that are right next to it. So it will pretty much figure out what the access time of data from each node is. And this will basically tell it how close the node is from the RDD, right? So then it pretty much, does the data pulling and pushing. And now we have the criteria where it really does minimal network trafficking, right? So here, consider we have a couple of items. We have about 25 items on the screen. And, the RDD here is split into 5 partitions of 5 each. So item 1 to 5 is partition 1, 6 to 10 is partition 2, 11 to 15 is partition 3, 16 to 20 partition 4, and respectively 21 to 25 is the 5th partition. So again here, as you can check out, if we are mapping it, we can cross map it to something else where we are pretty much using it as efficiently as possible, guys. And since Spark usually accesses distributed partition data, and to optimize all of the transformations, it creates the partitions that can hold a lot of data. So every partition is pretty much being created where it knows that it can hold a huge chunk of data, guys. So do we have to program how we partition the data? Well, absolutely not, because RDDs get partitioned automatically without a single intervention from the programmer, guys. But Spark pretty much gives us the functionality where we can go on adjusting the size, the number of partitions, or how the data has to be partitioned based on our particular application, guys. So this can be done using the def get partitions and array of partition method, where we'll be pretty much this is basically functioning on an RDD, and this will get to know the number of partitions that are present in the particular array, guys. So coming to the types of partitioning, we have 2 types of partitioning. One is hash partitioning and one is range partitioning, guys. So again, this is another step taken by the developers at Spark, where they're giving you the customization to partition it based on your particular needs. But there is a very important thing that you need to know is customizing partitions is only possible when you're using paired RDDs. So you cannot go about using this on single RDDs, guys. And but then, so this might feel like a disadvantage at this point of time, right? But it is not. So again, another basic advantage here is that pretty much you will have data which is very similar, right? So you'll have multiple cases of similar data which is located at the same place. Then shuffling the data pretty much in by transforming it by using group by key, reduce by key will again make it an efficient way to pretty much know that you have an index where you can pull your data from, you can arrange it, you can sort it based on that particular index element, and this is again an advantage of having paired RDDs as well. So coming to the hash partition technique, the hash partitioning again is pretty much the technique where one single key, we call it the hash key. So the hash key is basically used to distribute all the elements across the partition, guys. So one thing, I mean, you will not be using this practically, but I just found this to be an important concept that I want to teach you guys. So with hash partitioning, basically you need to know that we have something called as the hash key, guys. So the hash key is at the end of the day our go-to person, where we'll be using it to distribute our, basically we'll be using it to track, to create and to distribute all of the values in terms of different partitions, guys. So again, we have one single RDD on the top, we have a couple of elements in that particular RDD, and pretty much we'll be hashing it. We call it the hash key. So we'll be using the hash key to pretty much tell where where the particular key and where the element of that key has to sit and in which partition, basically. So all you need to know at this point of time is that the hash key denotes where an element has to go into which partition, guys. Coming to range partitioner, well, we already know that RDDs, they have keys, and sometimes these keys will have a particular order, say ascending order or descending order, and to go about doing this in a fashioned manner, instead of using a hash key, we'll be pretty much going about using range partitioning, guys. So range partitioning will work when you have something in ordered. So how do we go about doing it is basically we'll have tuple here. Our tuple will have keys which are in the same range as our native RDD, and keys in this particular range partitioners are actually partitions based on all of the sorted range of keys, guys. So you need to, the keyword that we are trying to highlight here is pretty much sorted. So the keys which are present here are partitions which are based on the sorted range of keys and the native ordering of the keys as well. So how do we go about doing range partitioners? Well, it's simple, guys. So first we need to compute a reasonable range boundary to our data, right? So we cannot have huge set of boundaries and work on it. Basically, it will take more time. Followed by this, we'll be constructing a partitioner, giving the partitioner that particular range boundary that we're using it, and telling it to partition our index and work with it from there. And lastly, we'll be shuffling our RDD values against this particular range values, guys. So we have a couple of tray numbers out here to give you as an example. We have the complete tray number and from where it moves. So central station, northeastern station, Bayview, and all of that. So you can pretty much observe that a value from the southern train has been put into another RDD out here, and a value from our first central RDD has been put here as well. So as soon as a new RDD is being created after using our range partitioner, it is being done in a certain order, but then you need to know that the values are being shuffled after the values are being changed, guys. Coming to the last concept of this particular module, we'll be checking out how we can pass functions to Spark, guys. So basically most of Spark's transformation and some of its actions, it basically depends on passing the functions that we have already seen, right? So we usually pass functions by adding it, we're sorting it, and we can use functions there as well. So each of the languages that we'll be working on, Python, Java, and Scala, they each have a different mechanism to allow the operation of passing a function. And in Python, we can pretty much pass one function inside another function, and you can have it under an anonymous setting as well, which is the lambda function that we'll be using, and a couple of other functional APIs provided by Python as well. But some other considerations that come into play here are the name of the functions that we pass, the data that we reference in that function, and if the data needs to be ordered, and if they need to be serialized, guys. So Spark's API, again, the most important point on this slide for you guys is that it relies heavily on passing functions in our driver program, so it knows what can be done and what should be done when it pretty much runs on the cluster, guys. So two recommended ways to go about doing this. First one is to pretty much go about defining an anonymous function. Basically it is a method which is used for any short snippets of code. But then what if you have a longer program or a longer set of code that you need to go about doing it? Well, sure, you can pretty much use an anonymous function as well, but then it is impractical to go about using typing it out in a single line. So we can use something called as static methods, where we'll be using global singleton object to go about doing this, guys. So coming to the first anonymous function, so basically it's a method we'll be using it for short pieces of code that I've mentioned. So one quick example for a short piece of anonymous function that we already discussed is the lambda function, guys. So lambda x, this function basically returns nothing but a sum of 2 to the input variable. So whatever is on the left of the colon is again the list of parameters that you need to pass, and on the right is the expression that which is required to involve all of the parameters and to perform operations on that. And you can name the functions as well. So as we already seen, 1 2 3 4 5 values and RDD is being created. We are creating the map function, and then we are having the lambda give us the +2 output of whatever is the input, guys. So functions take in multiple parameters, or the functions can take no parameters as well. So there's pretty much no compulsion that you have to compulsorily push in values to a function, guys. So as you can pretty much check this out, we are adding 2 to each of the elements here. So 1 + 2 is 3, 2 + 2 is 4, 3 + 2 is 5, and so on, right? So it is pretty much simple, guys. So with the anonymous status of this function, so as soon as you pretty much find it's basically saying is that it needs to init our main function and then get the value of x. So you can have the lambda function return the x + 2. It doesn't have to be as simple as x + 2 what we've shown here. But then you can pretty much go about doing it in more complex ways, again depending on your application as well, guys. So coming to static methods, let's say we have the quick example where we are defining an object. Let's call the object as my functions, and let's pass a function to it calling it as func1. So instead of just passing values to our function, what we can go about doing is pretty much we can do the call by reference as well. So if you have to revise call by reference quickly, then you can go about checking out the older module. But to tell you what call by reference means is basically the value gets copied into the formal parameter, and changes done inside the function pretty much reflect outside the function as well. So instead of having just one singleton object where you'll have to create another duplicate object and work on it, with respect to static methods, it basically requires nothing but just sending one single object, and it contains it basically that single object that you send will pretty much pull in and bring all of the class data mentioned along with it as well. So here's what a simple class looks like. Class name of it is my class. We have function 1. We have another function, it's called do stuff, and basically here what we're trying to do is we're creating an instance of the class, and we'll be calling the function of it, guys. So the do stuff method of it. So the map inside the reference is pretty much it's the func1 method, and the whole object. So as I showed you in the previous slide, the entire object has to be sent into this class, guys. So to give you a quick example with respect to mapping, it is exactly as similar as writing rdd.map, where we are mapping the same reference, this dot func1 of x, guys. So again, Spark is pretty much giving you the highest efficiency possible when you have to define an object like this, and when you have to pass the entire object towards the class, and you can pretty much go about mapping it using one single line, guys. Congratulations, you've come to the end. I hope you guys enjoyed this. So just before finalizing up, let us quickly walk through the quiz. You can take about 5 seconds as usual, and you can go about answering this. So which of the following is a module for structured data processing? Here's another question for you. So which is a distributed graph processing framework on top of Spark? I think this is a very simple one, right?
Just a quick info, in case if you guys are looking for end-to-end course certification in PySpark, IntelliPath provides the PySpark certification training program where you can learn all of these concepts thoroughly and earn a certificate at the same time. The link is given in the description box below, so make sure to check it out. I hope this session was very informative for you all. If you have any queries regarding this session, make sure to head down to the comment section below and do let us know there, and we'll get back to you at the earliest. On that note, have a nice day.